Hello, everyone. Welcome to the November 2025 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. I thought we'd do something different for the intro today. I'm going to elevate a question that was asked for the AMA up to the intro because, maybe this is something that would be interesting to do going forward because teasing people with one good question can get them interested in it. But in fact, in this case, it just sparked a separate thought in my brain that was not an answer to the question that works well for an intro. So the question is from One Armed Wolf, who says, simple question. What have been your favorite films this year, and do you have any strong recommendations? For my part, Sinners and One Battle After Another both feel essential in their own way. So the sad news is I don't have any great list of strong films this year. Sorry about that. Just have not been going out to movies these days. I feel bad about that because I am a big fan of movies, of cinema, of literally going to the theater, having the popcorn, watching the movies. It's just that my life this year has not been amenable to that particular activity that much. I did see Sinners. I thought Sinners was amazing. Everyone thought Sinners was amazing, so no special insight there. I have been spending time watching TV. Like at the end of the day, we will often watch a couple episodes of something before turning in reading or whatever at the end of a long day. That's a good way to unwind. So I know a lot more about what are the good TV shows this year. But again, I think most of my choices are more or less the standard choices. Everyone agrees that Slow Horses is brilliant. Murderbot was a lot of fun. I'm not going to list all of my favorite TV shows, but one of the ones that we've been watching is Only Murders in the Building with Steve Martin, Martin Short, Selena Gomez. I wouldn't say brilliant TV. It's comfort food TV. It's fun. It's funny. The acting is really good. The stories are kind of interesting. And it's about a podcast. So how can I not like it? And there's a lot of podcast jokes in there. But in fact, what I wanted to mention by way of the intro is that about a year ago, I had an idea to do a special solo episode of Mindscape where I would make up a fictional story and tell it as a podcast episode, a mystery story. And I had the idea that the title would be Only Murders in the Wave Function. You know where that came from. And the title is great. I'm very happy with the title. But in fact, the experiment did not go well. And I almost never, reveal my experiments don't go well enough to make it onto the air. There's not that many of them or anything like that. But, what one should do for an experiment like that is write the story, type it out, write all the words, and then read it. Do a dramatic reading of the story. What I was thinking was, who has time for that? I'm just going to sort of outline it, sketch out the characters, etc., and then I will extemporaneously speak the story like a storyteller. This is something that happens. This is something people are able to do. As it turns out, it is not something I'm able to do, or at least I have no practice at it and no special skills at it. And the final product, it didn't even get to be a final product. The product that I was producing was just bad. It was not really worth anyone's time listening to it. It would have turned people off from the Mindscape podcast. I think the idea is potentially good, but I think you just got to write the story. Writing a story by itself is a skill, is a craft. You don't not just automatically good at it, even if, like me, you've been writing plenty of other things for your whole life. There's special abilities, special things you have to keep in mind when you're writing fiction, okay? But then also the performance of it, the speaking of it, the idea that you would just have the outline and sort of spin a tale around it is another skill that I don't especially have or haven't really practiced. And in the case of a mystery story where you want to have clues and you want to be very, very careful not to give away too much, but to give away a little bit to sort of set up some red herrings and some false leads and things like that, you need incredible precision in exactly what you're saying. And that's not really available if you're just making up the exact words as you go along. So that didn't work, sadly. Only Murders in the Wave Function. The title is so good, I got to do something with that, right? I have to do something. Don't be surprised if at some point over the next year or two, there is a solo podcast with that title, even if it's not exactly what I had in mind doing in the first place. Several years in to making the podcast, I think it's good to experiment, to freshen things up occasionally. I haven't done that yet, but I'm going to do it at some point. Anyway, thanks for that question, One Armed Wolf, and thanks everyone who submits questions to the AMAs. We do these once a month. The questions come from Patreon supporters of Mindscape. So if you would like to ask a question. People keep asking questions who are not Patreon supporters. They ask them, on social media or wherever. And I'm like, yeah, that's really not how it works. This is a reward for being a Patreon supporter. There's not a lot of rewards. You get an ad-free version of the podcast. I do a little reflection for like 4 or 5 minutes, audio after every podcast that is for Patreon supporters only. But mostly it's out of the goodness of your heart. Mostly it's that I appreciate the Patreon supporters. It makes me think that there are people who are really dedicated to it. Spending $1 for an hour-long podcast episode doesn't seem unreasonable to me, or whatever you want to spend. So you could go to patreon.com/Sean M. Carroll and join up if you wanted to do that. Everyone gets to listen to the AMAs, so that's the bargain that we all make. There's people who are supporting the operation, and then there are free riders, and we love them all. The free riders are great. I know that not everyone is in a position to spend their hard-earned cash on podcasts these days. What I should do, and what I never do is encourage people to spread the word about Mindscape, to go to, I don't know, where you put reviews of podcasts these days. Is it on iTunes? Do they still do that? I really don't know. I spend a lot more time making podcasts than listening to them. Sorry about that. But, get the word out. I love it when people just randomly on the street say, oh, yes, I know your podcast. That's a good feeling. And I hope that the people who are out there listening to it get a good feeling from it also. So let's go. Philip Ricius says there has recently been a public call for a prohibition on the development of superintelligent AI, signed among others by Jeffrey Hinton and Yoshua Bengio. What is your take on such statements and the subject matter? Well, that's two different questions, right? But I get it. That's fine. The statements, I like statements in a sense. I think that making statements in the sense of a public statement with a lot of people signing, open letters and so forth, can be a good way to get words out about important thoughts. I'm kind of reluctant to sign them myself because one person writes them and then everyone else signs them. And, I don't like signing things that other people have written because it's never exactly what you would have said, right? So I'm a little reluctant, but sometimes I do it occasionally myself. I'm not sure that it has much of an impact. I've seen open letters that have been talked about a lot to be made fun of more than ones that actually made a positive impact. But, you got to try. We got to do what we got to do. The specific subject matter of a prohibition on superintelligent AI, I have mixed feelings about at best. To me, it seems like very much good intentions aimed in the completely wrong direction. Superintelligent AI is not the threat in my mind. I get the arguments that it is. I'm just entirely unconvinced by them. I do think there's plenty of reasons to be worried about AI. But it's the artificial stupidity that I'm worried about. It's AI being given responsibility over things that are super duper crucial and important, taking human beings out of the loop in ways that the AI might not be trustworthy for. That's a huge problem. We're already seeing it. It's right in front of our faces. I've seen no threat from superintelligent AI. I think that, in fact, the very phrase superintelligent AI is entirely wrong-headed. As a phrase. It implies that there is something called intelligence that has a unique meaning that is spread along many contexts, which I don't think is true. I think there are different abilities that often get correlated in human beings, and we call them intelligence, but there's no reason for them to be similarly correlated in artificial agents. And the prefix super implies that there's sort of linear scale on which we judge intelligence. And at some point, AI is just going to become better than us at all of those, which is not right either. It's super duper clear to me that we've built, I've said this a million times, you don't need to hear me say it again, but we've built these programs that are 100% designed to act like human beings. To act like they're thinking like human beings, to talk like human beings. But they're clearly not doing the same thing that human beings are doing, and it's just a mistake to anthropomorphize them overly. It's very important to understand their capabilities and their shortcomings. That's super duper important. But this simplistic idea that since we grew up talking to other human beings and rating them on their intelligence, we should just do the same kind of thing when a computer program comes along, when a predictive, token prediction, next token prediction mechanism comes along. That's just super duper wrong. It's like saying, oh yes, they're building nuclear weapons, and I'm very worried about the threat of nuclear weapons. And someone says, oh, what is your worry? And the answer is, well, if you stand next to the nuclear weapon, I'm worried that the radioactivity will mutate my genes and turn me into a lizard person. Well, there is a threat from nuclear weapons, but it's not that one. I think there is a threat from AI being deployed badly, but it's not the one that people are talking about. In the AI sort of informal chit-chat world, there's all this talk about, what if the AI becomes so important and it's very evil and it's so smart that it can talk its way out of whatever you want to do to it? Because ordinarily you'd say, like, if an AI starts behaving badly, I unplug it, right? Or I remove it from all of its affordances out there in the physical world. And the response is, oh no, but it's so clever that it will convince you not to do that. There's this feeling that if the AI becomes super important, it will just reason circles around us and we'll be unable to resist its charms. And I'm just thinking, like, have you ever met an intelligent person? Have they ever had the ability to just convince you of anything that they thought was true? Like, what is this world you live in where not smart people simply believe things that smart people say? Like, I don't live in that world. I'm kind of glad I don't live in that world, but in some ways it would be a better world. Not to mention the fact, like, if you did believe in this weird concept of superintelligent AI, are we sure it wouldn't be awesome? Like, what if it just cures cancer, fixes our political problems, and, causes great prosperity in the world? You want to delay that? I think thinking about the prospects of AI, which is really what the people signing the statement are getting after, is super important. Thinking about what exactly it can do, how exactly it will be employed. People are rushing to put it everywhere because they want to make money, and I think that the rush to put it everywhere is a huge, huge mistake. We absolutely do need to worry about it and think through what the prospects are. But to phrase it in the bundle of superintelligence and a worry about that is, I think, doing more harm than good. M. Hayes asks a priority question. The Patreon supporters who ask the AMA questions have the right to, once in their life, ask a priority question, which I will promise to do my best to answer. Sometimes my best is not going to be very good. Too bad. You only get one priority question in your life, but I will honestly do my best. So this one is the following. From M. Hayes. Entropy is often described using the example of a glass of black coffee into which you mix white milk. At first, you can see the milk and coffee separately. That's low entropy. As it mixes, it becomes a consistent tan color, which is high entropy, so entropy is increasing. Suppose, though, both coffee and milk were the same temperature and we only saw an infrared. We'd see nothing changing. Entropy would be constant. So is entropy relative to the observer? Carlo Rovelli seems to imply that it is. Is that a generally accepted viewpoint? If not, can there be a better definition that doesn't depend on our specific senses? If it is relative, what does that mean with respect to things that depend on entropy? Are they relative to by definition? That's almost correct. I wouldn't say it's exactly right. Entropy is relative to a coarse graining. Entropy is relative to your particular definition of what counts as the macro states that you're grouping all the microstates of the system into. So if you were counting in your macro states where the cream molecules are and where the coffee molecules are in some coarse-grained way, then the story you told will be the correct one. When they're separate, they'll be low entropy. When they're combined, they'll be high entropy. If you're not including that, if you're just judging the entropy of a system, if you're making up your coarse-grained macro states by just measuring the temperature and the pressure, then those what we were talking about as low entropy states might not count as low entropy. As long as the temperature and pressure are uniform throughout, we would call it high entropy. So it's 100% true that entropy depends on your coarse graining, and in some sense, human beings make up the coarse grainings, right? So in that sense, it's subjective. There's a definition that comes into it that could have been otherwise, but so what? That's fine. That's a feature of entropy. It's not a bug. Again, this is something I've said many times, but you're not Laplace's demon. I think I should write a book called You're Not Laplace's Demon. Or if not, maybe a spoken word album called You're Not Laplace's Demon. But the idea is that you don't see all of the microstates of the system. You don't see the positions and velocities of everything. You see some coarse-grained features. That's what you naturally see. If you were able to see everything, you would just be Laplace's demon. You wouldn't need to talk about entropy or temperature or pressure. You would just know what's going to happen next. But you don't. So entropy is a useful concept precisely because we have to coarse grain. Now, indeed, two different observers might choose to coarse grain differently. They will find slightly different answers. But the fact is, they won't be that different, those answers. They won't be radically different unless you really, really work to concoct some scenario in which it artificially is like that. Roughly speaking, even with small variations in our definition of the coarse grainings, everyone is going to agree on which is low entropy and which is high entropy. So I think that's perfectly well understood, perfectly well known. That's just something that is a feature of entropy, just like it's a feature of temperature, right? We define temperature in a certain way. The only difference between temperature and entropy is we've all agreed on the definition of temperature. But, what if someone doesn't want to agree? then we would have a disagreement, but that's okay. It's not like the world is changing. It's just that we're using different words to describe it. Ryan says, I was one of those undergrads yelling, "But what is a measurement?" at the quantum mechanics textbook. I wasn't after a deep interpretation, only intuition for when they occur, as it is mostly evident when a Newtonian applied force occurs. In practice, physicists cannot predict experiments without having a rule set for when measurements occur. So what is their rule set? Is it fair to say it's a mix of analogy to past experiment and a haphazard application of distinguishability? I actually think that the definition of measurement is more clear than that last suggestion makes it sound. It is true that in the ordinary textbook / Copenhagen version of quantum mechanics, no explicit definition of the word measurement is given. But remember, we've been able to go 100 years doing quantum mechanics and making hugely successful predictions about things. How is it possible that we can do that without defining what this word means? And the answer is you know it when you see it. And the reason why that's a perfectly good way of going about it is because human beings are gigantic macroscopic objects with, 10 to the, how many particles do you have in a human body? 10 to the 28, something like that? I really don't know. But there's a lot of particles in your body, and also you're warm, right? So you're radiating in the infrared. And what all this means is that human beings are not isolated from their environments. So if a human being sees something quantum mechanical, that is to say measures something quantum mechanical, that human being becomes entangled with the different possible measurement outcomes, but then decoheres right away. Because you can try your best to, hook up an apparatus that is like very tiny, very isolated from the environment, measures some quantum mechanical thing and becomes entangled with it, because what it means to measure is to become entangled. But then also, there's two things that happen in measurement. One is an apparatus becomes entangled with the thing it's observing. The other is that the apparatus decoheres. You can try to prevent your apparatus from decohering by becoming entangled with this environment, but at the time that the human being sees it, it's always too late. The human being is going to decohere right away. You cannot prevent a human being from decohering right away without killing them, because you have to stop them from radiating. How are you going to do that? You're going to cool the human being down to close to absolute zero, and that's not going to be a useful observer anymore. So once it's at the level of what a specific human observer sees, when a measurement has occurred is perfectly obvious, right? All of the ambiguity comes down at the microscopic level, where decoherence is much less evident. So none of that is an excuse. I think that you need to define measurement at the end of the day, but you also need to understand why you could get away without defining it for so long. Jason Turner says, lacking any major explanation of consciousness, how can we be confident that even dumb, non-general AIs are not somewhat conscious, and thus that we are not using them unethically? Well, interestingly, people have argued about this. Like, it's not at all agreed that we aren't being mean to the AIs and that isn't bad. I personally think it's kind of silly. It is true that we don't have a complete explanation of consciousness, but that's not the same as saying we have no idea what's going on in consciousness, right? AIs are very manipulable, as the Grokopedia example shows us. I don't know if any of you have seen this. Elon Musk has unleashed Grok, which is his version of an AI large language model, and it has made an entire version of Wikipedia. Okay, so it basically a lot of it is just copied from Wikipedia. That it's told not to put any links to Wikipedia in it, so you can't tell that it's copied. But then it adds a lot of more racist and controversial and conspiracy theory stuff also, because you can tune it to do that, right? So anyway, all of this is just a reminder that we control the AI more than the other way around. In a million different ways, the AIs that we're dealing with these days are nothing like conscious creatures. They're only like conscious creatures sort of at the end of the black box output situation. They can pass the Turing test. I think that people argue about whether they can or not. I'm completely willing to say that an AI could pass the Turing test. These days, that's been a great accomplishment. That's really, really impressive. But that doesn't mean that it's conscious in any way. It doesn't have the same kind of inner life that human beings have. Does it have a different kind of inner life? I doubt it. Like, I've never met an AI that got bored or irritated or whatever. It can act bored and irritated, but it's clearly an act. I think it's pretty transparently just acting that way, because you can just tell it not to and it'll change its mind right away. Changes its mind. You see, you can't help, it's not changing its mind, but you cannot help but use those words, because all of our experience is with ordinary human agents, so we apply the same terms to the AIs incorrectly. I do think that there's a huge question about when will we know whether or not an AI that is much closer to becoming conscious really has and deserves rights and things like that. I think this is an absolute high priority task for some combination of philosophers and computer scientists and psychologists to really think about, and some of them are doing it. But this is an example of showing how hard philosophy really is when you don't already know what the answer is ahead of time. So I think that it's a question that should be asked, but I don't think that we're quite on the verge of needing the answer right away. I'm going to group two questions together. There's a lot of grouping today. I don't know. There's a lot of similar questions, so that happens sometimes. Ryan Nichols says, do you think the black hole area law and related bounds mean gravity enforces a finite number of degrees of freedom in any finite region, a genuine UV regulator, or are infinities in quantum field theory and general relativity simply artifacts that a better theory or renormalization removes without such a cutoff? And Brent Meeker says, in Mindscape 63, I love the fact that people are still listening to Mindscape 63. Good for you, Brent. Finding gravity within quantum mechanics. You speculated that there are only finitely many degrees of freedom in a given volume. Wouldn't this imply that there are also only finitely many possible states, and so there would be a smallest non-zero probability of any possible event? In the branching picture of ever-ready quantum mechanics, branches would be pruned by falling to a probability lower than this smallest non-zero probability. So these are not quite the same question, but you see how one leads into the other. The issue is, how big is Hilbert space? Hilbert space is the space of all possible quantum states. And if you have a single spin, a single qubit, you have a two-dimensional Hilbert space. You can think of the dimensionality of Hilbert space as basically how many distinct measurement outcomes could you get? For a spin, the answer is 2. You can get spin up or spin down. For a spin 1/2 particle. For a spin 1 particle, you could get 3, and indeed there would be a 3-dimensional Hilbert space. That would be spin +1, 0, or -1. If you ask about the position of a particle moving in a potential, the very first thing one learns in a quantum mechanics course, how many different measurement outcomes are there? The answer is infinity, because it's a position, right? It's a number x from -infinity to infinity. Now, there's a subtlety there that we're not going to get into. There's a various mathematical subtlety about the difference between a countable infinity and an uncountable infinity. Really, it's a countable infinity number of possibilities, even though it looks like an uncountable number. So that's a tricky thing we're not going to get into. But okay, I can mathematically define quantum mechanical models, some of which have a finite number of possible states, some of which have an infinite number of possible states, where by possible state I mean truly distinguishable states. I can always take a linear combination. Even in the single qubit, where I have just up and down, I could also take 1 over square root of 2 up plus 1 over square root of 2 down, right? There are an infinite number of possible states even in a two-dimensional Hilbert space, because a two-dimensional vector space still has an infinite number of vectors in it. It only has 2 orthogonal vectors at any one time. Now, if I have a system in quantum mechanics has an infinite number of degrees of freedom, an infinite dimensional Hilbert space, and I take a subset of it, I can get infinities all over the place, like infinite entropy in that subregion or whatever it is. But it turns out that gravity seems to give a genuine cutoff. It's not really an ultraviolet cutoff. It's an energy cutoff. It goes back to classical black hole arguments. If you can't put more energy in a region, then it would take to make a black hole, because if you try to put more energy in, what happens is the black hole gets bigger. So there's literally an upper limit on the amount of energy you can have in a region of a certain fixed size, given by how much energy the black hole would have in that region. And black holes, according to Hawking and Bekenstein, have a finite entropy, and even though it's the largest possible entropy you can put in that region. So this strongly suggests that the dimensionality of Hilbert space that describes the black hole is a finite number, not just a countably infinite number. And I more or less agree with that argument. It's not by any means airtight, because it's quantum gravity, and who knows, there could be some subtleties in there that we don't understand. But I think that's basically on the right track. I even wrote a paper saying exactly that, but it wasn't, an original research paper. It was just one of these essays for the gravity research competition, where you sort of summarize some argument or, put forward a clever idea or whatever. But many other people have said it. It's certainly not original with us. Tom Banks recently wrote a paper saying exactly this. Other people have said, no, the black hole entropy is really the extra entropy over and above the infinite amount of entropy that you already have in empty space. So maybe there is an infinite number of degrees of freedom in there, but the black hole just has a finite extra number that you're putting there by making a black hole. That doesn't sound right to me, because these purportedly infinite number of extra states have no effect, or invisible, or are not actually doing anything. So I think for all intents and purposes, gravity is a regulator that does mean that there's only a finite number of degrees of freedom in any region. To Brent's question, that does not mean that there's the smallest possible probability, because remember, even for the qubit with only 2 degrees of freedom, I can take alpha times spin up plus beta times spin down to make a linear combination, which is a perfectly good state. And then the probability of measuring spin up is alpha squared. The probability of measuring spin down is beta squared. So alpha squared plus beta squared equals 1. But the fact that there are 2 dimensions of Hilbert space doesn't tell me what the value of alpha is supposed to be. The probability depends on the value of alpha, not on the number of dimensions of Hilbert space. So you got to be a little bit careful when you move between people saying finitely many possible states. Usually what they mean is 100% distinguishable states, not really there's only a finite number of possible states. Anonymous says, I have a strong interest in natural philosophy, particularly the foundations of physics. My problem is I want to figure out how much detail I need to go into while studying physics. I get that I need to do problems. I'm not trying to be anti-math. But at the same time, is practicing a few hundred integration by parts problems going to make me a better natural philosopher? The advice I'm getting from most physicists is that the best physicists are going to make the best natural philosophers. But I'm skeptical of that answer, because it seems to me that the best physicists are not always the most interesting from a philosophical point of view. What's your view on this? Is there a point where I'm getting lost in the weeds? How do I figure out where that is? Or conversely, how do I figure out that I'm not good enough at the calculation to have a right to an opinion? Well, I know that the last question there is a little bit tongue-in-cheek, but everyone has a right to an opinion, right? There's no criterion of being good enough at doing contour integrals so that you become enough of a good physicist to have an opinion. One should always gauge one's strength of opinion to one's strength of knowledge, right? If someone who is much more knowledgeable than you has a different opinion than you should take that into account. You should say, well, okay, I have my opinion, but this person knows more than me. Their opinion is different. Maybe I'm wrong, but I still have my opinion. That's how we should reason about these things. Whether or not you need a lot of mathematical knowledge to be good at natural philosophy, at understanding the foundations of physics, I think is one of these difficult to answer questions, because just for the simple reason that everyone is different. Everyone's style is different. Everyone's specialty is different. Everyone's interests in what matters is going to be a little bit different. There are people who are philosophers of physics who are super duper mathy, right? There are people who are, their job description is philosophy of physics. They're employed in philosophy departments, but their papers are much more mathematical than the papers of a typical physicist. That's just the style that they use and that they like, and that's fine. There are other philosophers of physics who are very, very good, who are not like that, who it's mostly still words, just like in other philosophical papers in other subdisciplines. So all else being equal, the more practice you have doing the math, the better you will be. All else being equal, the more you know about Kant and Hegel, the better off you will be. That doesn't mean you need to know Kant and Hegel to be a good philosopher of physics, right? I certainly don't know enough about those people to be called an above-average expert in those particular fields, but all else is not equal is the problem. So you don't have an infinite amount of time to study things. When you're a young physics student, like I once was, as an undergraduate or graduate student, there's absolutely a feeling that one can get, if you're interested in theoretical physics, that the more math I take, the better, right? And I took a lot of math classes for exactly that reason. And it's true that the more math you take, the better, except the knowledge that there's other things you could be doing with that time. Like maybe you could be learning more physics, or maybe you could be doing physics or doing research, which is not to say you shouldn't learn the math, but there's a balance. So I can't really answer the question in any definitive way, because it's going to depend on exactly how you'd want to do the natural philosophy and what kind of philosophy you'd want to do and how you want to think about it and all those things. All else being equal, yes, the more contour integrals you do, the better off you're going to be, integration by parts or whatever. But there's a limit past which, there's a point of diminishing returns. Jacob says, I'm having trouble understanding how we ended up with a universe that has an equal number of protons and electrons. Is there some process that ensures they're created in equal amounts? Well, there's definitely not such a process, because they don't have to be created in equal amounts. In fact, we don't have exactly the same number of protons as electrons. Off the top of my head, I'm pretty sure we have more electrons than protons. Why is that? Because we have some positrons in the universe, anti-electrons. We have almost no antiprotons in the universe. Positrons are much lighter than antiprotons. They're easier to make. So the point is, what we really have is an imbalance between matter and antimatter, or at least I should say between baryons and antibaryons. Why do I say baryons and antibaryons? Baryons are the protons, neutrons, those heavy particles that carry the strong nuclear force. And there's a pretty good symmetry of nature, which is baryon number. It's not an exact symmetry, but it's very good in the low energy universe in which we live. So when you have a conserved quantity like baryon number in the universe, then once you sort of decay to the lightest particle carrying that quantity, there's no other place it can go. So if we have, for reasons we don't understand as of right now, more baryons in the universe than antibaryons, then any antiprotons that you have hanging around will annihilate with the protons. The protons will be left over. Any heavier baryons that you have, like neutrons, for example, will generally decay to the lighter baryons, namely the protons. And so you have some number of protons out there in the universe. But also you have conservation of electric charge. Electric charge is another quantity that is conserved. So you can't just have a bunch of protons without some negatively charged particles. So the question you should ask yourself is, what is the lightest negatively charged particle that I could have in equal number to the proton so that the net charge is zero? And the answer is the electron. Heavy particles always like to decay into lighter particles, The only thing stopping them is when there's some conserved quantity. So electrons are the lightest particle containing electric charge. Protons are the lightest particle containing baryon number. So those two particles basically carry all the baryon number and all the electric charge in the universe. The total charge is 0. That's why we have approximately equal amounts of both. Miran Mizrahi says, I'm going through the Theoretical Minimum lectures. These are the books and online lectures from Lenny Susskind, former Mindscape guest Lenny Susskind. Often Susskind says something like, I am going to assume the Lagrangian to be ... and lo and behold, it ends up being right. I get that this is pedagogy and that he knows the answer, but why does it work? Does it work like this in real life? You invent a Lagrangian and check until you get one right, and has use of AI on trying to, given a system description, come up with a Lagrangian been increasing? Yes, this is more or less what one does as a theoretical physicist. I've certainly guessed a whole bunch of Lagrangians in my life. You can look through my papers. My very first paper has a guessed at Lagrangian in it, as do many others. And you hope to be right. Being right is really hard. Einstein got it right. Hilbert guessed the Lagrangian, but Einstein had the theory that the Lagrangian came from. Weinberg got it right. Stephen Weinberg got it right for the electric weak theory. Maxwell got it right, but there's a very finite number of people who guessed correctly a Lagrangian that actually does describe the real world. There's a bunch of people, of course, who guessed the Lagrangian for the Higgs particle back in the day. But that's what you do. What else are you going to do? I mean, this guessing process is nothing other than scientific hypothesizing, right? And the thing that you guess in traditional quantum field theory is the Lagrangian. For those of you who don't know, I'm sorry, I assume everyone has read Quanta and Fields, so they know what Lagrangians are, or they even reading Space-Time in Motion would have been enough for you to know what a Lagrangian is. The Lagrangian is just the most compact way that you can state the dynamical laws of this new theory of physics that you're inventing. So yeah, very often in physics, you either guess a Lagrangian or you guess a quantum state, a wave function, right? Bob Laughlin won the Nobel Prize for guessing a wave function. If it turns out to be right, that's kind of all you need. And then you check it. You guess, then you check. You see if it works. That's exactly what science does. Has the use of AI to come up with Lagrangians been increasing? Not that I've seen at all. Again, this is exactly what AI would be bad at. AI is really good at doing data analysis that could have been done anyway, right? Like if you already have a data analysis pipeline, AI could do that. But guessing Lagrangians, going outside the training data to guess at something creative and new is exactly what AI is bad at, and for very obvious, predictable reasons. So that's not the kind of way that I would use AI to do theoretical physics. Not to say that it can't eventually be used that way, but that's exactly what large language models are not really tuned to be good at. Kelowna says, as a practicing data/machine learning engineer, while trying to improve my stats skills from this wonderful book, Learning Statistics with R is another programming language, I run into this chapter on research design and different ways on how things can go wrong, biases, different effects, fraud, deception, self-deception. As a real-time researcher, how do these affect your work and physics research in general, and how do we try to mitigate them? First, let me say that I don't know about that book. I don't know anything about R. I haven't used it. I've used Python a bit, but never R. But I love the idea that this book has a chapter on research design that goes into all those things, because these are super important topics. And usually in the training of a scientist, you sort of pick up ideas about these topics, biases, deception and self-deception, informally. You don't get a lecture on them or a course on them or read a book that talks about them. You just sort of absorb them from the environment around you, and maybe that's too bad. Maybe that leads to a little bit more self-deception than there should be. Look, these things are everywhere, but they're not scientific features. They're just human features. Biases, fraud, deception. These words exist outside the scientific context. The good thing about science is that it does have checks and balances that prevent you from going too far with your biases and deception. You can go pretty far, don't get me wrong. You can absolutely go quite far, but eventually you're just not going to agree with the data in ways that no one can quite deny, and people are going to give up on it. So I do think I think there'll be another question a little bit later on that's related to this. Physics is probably the science, physics and chemistry maybe, where it is hardest to trick yourself with these kinds of biases and deceptions because it's too easy to do the experiments. In the social sciences, it can be very hard to do the experiments, and therefore you can get away with tricking yourself a lot more. The kinds of biases and deceptions you have in the physical sciences are also different than in the social sciences, right? To really be convinced that there can't be action at a distance. What is that? Is that a principle? Maybe it's just a bias, right? Like, how do you know there's not action at a distance? Like, in some sense, we should let nature tell us what it's doing rather than tell nature what to do. But in another sense, these intuitions that we have that you can think of as biases are actually 100% valid. As long as you're willing to change them once it becomes necessary to change them because the data are speaking in such a way that you can't ignore it, these intuitions that we have about how the world would work guide us in designing hypotheses, in the guessing that we were just talking about. Human beings do guess Lagrangians and quantum states and other models for other kind of scientific systems, but we don't guess randomly. We guess in certain directions because we think that certain kinds of theories and mechanisms are going to be more plausible, more promising, more useful, more fruitful, more likely to be true than others. So it's absolutely good to have biases that push you in creative directions as long as you don't let those biases get in the way of changing your mind when it turns out that your thing is not working. David P. Reichert says, for one of the fine-tuning problems, he said that it could be solved by positing the existence of another field, yielding a dynamical explanation. Do you think adding new fields to make things work is in some sense just as arbitrary as tuning the numbers just right, or is that different? It is different. So it could be different. It should be different, and it is different in the cases that people know about and care about, because you could propose a new field that has no fine-tuning in it, right? There are fields and there are fields. There are fields that do something in a very robust way, and there are fields that you just picked in a very delicate way to get something exactly right, and that's a little bit less convincing. The classic example of a field that does a good job is the axion field, which, by the way, we don't know if it exists, so it's still hypothetical. Still, I think it still has a good chance of existing. It's just it's hard to see because it very weakly interacts with the rest of the universe. But people noticed the following fact. They noticed two facts at different times, and this is in the 1970s when really the salad days of understanding quantum field theory and non-perturbative effects in quantum field theory and the strong interactions in QCD in particular. So one thing they noticed is that it would be very easy to guess a Lagrangian, as long as we're guessing Lagrangians, that would describe the dynamics of gluons, the strong interaction, the QCD dynamics, in such a way that it would violate CP. CP is charge parity conjugation, charge conjugation being switching particles for antiparticles, parity being switching right-handed orientations for left-handed orientations, looking at the thing in the mirror. So it was known that CP is violated in nature. It's a very tiny violation. Cronin and Fitch won the Nobel Prize for discovering it, but it's a little bit of violation. And as far as we know, the violation of CP in nature comes from the weak interactions. But it turns out it would have been easy to put it in the strong interactions, but it's not there. There is a parameter that you can invent in your guessed Lagrangian. It's called theta QCD, the theta, the Greek letter theta. It's called theta QCD because it takes the form of an angle. Theta and theta plus 2 pi would give you exactly the same physical effects. So theta sort of is like the angle that you are on a circle, right? Between 0 and 2 pi radians. So theta QCD could be any number from 0 to 2 pi. You go out there and measure it, and you don't detect it. It's not there. It's less than 10 to the minus 9. That sounds like a fine-tuning. And this fine-tuning is called the strong CP problem for obvious reasons. Strong interactions, CP. Why don't the strong interactions violate CP? That's the problem. They also discovered something else. If you take you do what physicists like to do. You imagine a box of gas at high temperature, right? So you have, and the nice thing about your imaginary boxes is you can make them as high temperature as you want, and the box is not going to melt because it's an imaginary box. And what you do is you ask, what is the energy density in the box? Okay, so this is just calculating the vacuum energy of empty space, right? And we know that the vacuum energy is naively infinite. Anyway, it's very big in your calculations. It should be small to be the cosmological constant. Okay, but forget about all that. All you want to ask is, how does the vacuum energy change as you change theta QCD? What is the lowest energy point? Is there any dependence of the vacuum energy on the value of the CP violating imaginary parameter in the strong interactions? And the answer is yes, there is a difference in energy depending on theta, and the minimum of the energy is at theta equals 0, which is what we measure. Okay, because we measure theta is less than 10 to the minus 9. By now, it might be 10 to the minus 10. I don't know. My parameter best measurements are a little bit out of date these days. But still, it could have been any number between 0 and 2 pi, and it's very close to 0. And you notice that the minimum energy is close to 0. But so what, right? There's no principle that says that this constant of nature should take on a value that gets you the lowest energy, right? Why should it? Well, one possible reason it should is, what if, there's different ways of saying this, what if you invent a new field that contributes to the effective observable value of theta, right? So you invent a new field phi with the property that when you measure the CP violation in the strong interactions, and the way that you measure that is by looking at the magnetic dipole moment of the neutron, actually. That's the easiest way to do it. So there's a tangible experiment you can do. Electric dipole moment of the neutron. Yeah, sorry. Who cares? But yeah, I think it's the electric dipole moment, EDM. And it's very easy to write down, not very easy, but it was done by Pache and Quinn, Roberto Pache and Helen Quinn. Helen Quinn passed away recently. She was a great particle physicist. They suggested that you could easily add a field such that this field phi would contribute to the CP violation in the strong interactions, such that what you're actually measuring is not theta QCD, but the combination theta QCD plus phi. And it's that combination that enters into the energy of empty space. So what this means is phi has a potential. Phi has a minimum energy state when it exactly cancels theta, so that you would observe the effective theta to be close to 0, which is what you do observe. So it robustly naturally happens. So you're basically taking something that was out there in the universe, the dependence of the energy of empty space on theta, and you're turning it into a dynamical thing that can allow itself to relax down to 0. So you had a fine-tuning, and now you don't have a fine-tuning. And I think that's completely legitimate. It's a different kind of thing. You're not just adding things willy-nilly. Brendan Barry says, in quantum field theory, many ideas in quantum mechanics are shown to be discoverable from taking the path integral approach seriously. In your opinion, does this formulation of quantum field theory have any ontological standing? Are the infinite number of paths at all related to the many branches in many worlds? Well, I have mixed feelings about this, honestly. So on the one hand, it's completely true that the path integral formulation of quantum mechanics is very useful in quantum field theory. So for those of you who are not familiar, the path integral is a famous idea due to Feynman, who, it's not a new kind of physics. It's just a new way of solving the Schrödinger equation, basically. The Schrödinger equation says, if I have a quantum state at one point in time, how does it evolve to be a quantum state at another point in time? And it's a very straightforward, ordinary kind of physicsy equation. It's a differential equation. You can solve it. You know how to do that. Makes people happy. Feynman said, look, let me imagine something else. Instead of saying I have a wave function for the position of a particle, let's say, imagine I have a particle, and the particle has a position. And when it travels from one point in space to another point in space over some period of time, rather than following a given particular path, what quantum mechanics says is the particle takes every path. It takes every path equally. But then there's an integral you can do, the path integral, because you're integrating over all the paths, that sums up the contributions to this path integral from the different paths. And when the path is almost the classically allowed path, all of those contributions add up in phase so that they give you a very noticeable probability, whereas if you're very far away from the classical behavior, the different paths tend to cancel out. So this is the path integral approach to quantum mechanics. And by the way, Feynman invented it in part because he wanted to solve the cosmological constant problem. He knew that if you took quantum field theory seriously, you would get a huge energy density in the vacuum. And he literally wanted to replace quantum field theory with particle physics, the particles being the most fundamental thing. It didn't work out. It turns out that the path integral is actually more useful in quantum field theory than rather as a replacement for quantum field theory. But the question is, okay, this sounds completely different than what we were doing. It sounds completely different than what we were doing. The path integral and the Schrödinger equation sound completely different in exactly the same way that the principle of least action in classical mechanics, which says that the system takes the path of least action between 2 points, sounds very different than Newton's laws, which say that a particle or a system is simply pushed around by forces and F equals ma. But it gets exactly the same answers, right? So which is right? Is there any ontological standing? I can't imagine any ontological standing one way or the other if two equivalent mathematical formulations give all the same answers to everything. Like, how could I choose between one or the other? I think it's important to have different formulations because they can be suggestive about how to go beyond what your current successful theory is. But right now, as far as we know, the formulations are more or less precisely equivalent. If you do think, we were just talking about the possibility that Hilbert space is finite dimensional because of gravity, that makes the path integral much harder to do and to make sense of. So it might be less fundamental, if anything, although that's completely speculative. We don't know the answer to that right now. The final thing is the infinite number of paths are really not related to the many branches in many worlds, at least not in my way of thinking about branches. In my way of thinking about branches only exist once they decohere from each other. There's an infinite number of different paths. Whether or not they decohere is completely irrelevant. Indeed, in all the interesting cases, they don't decohere from each other. So the paths in the path integral, there's many more of them, and most of them don't decohere. They're not the same as the branches in many worlds. But that's not necessarily the only way to think about it. Branches, as you know, I always say this, look at even if you don't buy the book, read the title page of David Wallace's book, The Emergent Multiverse. It's about many worlds, and the word emergent is there in the title because he's trying to emphasize that the branches are emergent, okay? The worlds are emergent. They're not actually objectively defined by the theory itself. They're a way that we human beings can talk about it at a higher level. Stevie CPW says, LSU, Louisiana State University, recently fired its head football coach and it's been reported that he will receive a contract buyout of $54 million. How do you feel about this? I feel I would like to have a buyout of $54 million, but that's not very realistic. Not everyone can have those kinds of buyouts. Look, I think that this is actually a pretty subtle and complicated question, and here is an example of where it makes sense to know the limitations of one's knowledge. At first glance, the fact that, number one, a public university, Louisiana State, is paying such a huge amount of money to its football coach rather than putting money into education and research and academics rubs certain people the wrong way. I get that. I very much think that the first mission of universities should always be education and research. On the other hand, they make a lot of money from football. It's a major football program. A lot of people go to the games, watch on TV, buy the sweatshirts, and whatever. Is football at LSU overall a money-making story or money-losing story? I honestly don't know. I'm willing to admit that I do not know that, and I don't really care enough even to go try to figure it out. Whether or not the economics of paying a high-level football coach that much money at a public university is a good investment that gives other benefits to the university, or is simply kind of a boondoggle because certain members of the alumni want football. I mean, look, maybe losing money on giving a big salary to the football coach is worth it because it makes some donor donate $200 million. I truly just don't know. So I think that there could be something really, really bad about this that deserves closer scrutiny, but I don't know that there's anything bad about it. It could be all just, the price of doing business, and sometimes you bet and you lose. Like, that's what life is like. Muffin asks, I was recently given a lecture on the issue of p-hacking within science. While this seems to be much less of a problem within fundamental physics, fields such as medicine and psychology appear far more affected. I would love to hear your thoughts on the broader implications of this. Should we be worried that modern scientific culture somewhat incentivizes false positives? Yeah, possibly I should have grouped this one with the previous one, with the earlier one rather. But again, I think that this is an issue, absolutely, in science. P-hacking, for those of you who don't know, in some areas of science, not so much in physics, but we use the variable p to talk about the statistical significance of a result. And you want a certain statistical significance in order to get your result to be published. Of course, if there's a probability of getting that result just by random chance, the whole idea of P of this statistical significance is you want a result that will be unlikely to happen by chance. But you can get unlikely results by chance to happen just by doing lots of experiments. So P-hacking is you just do the experiments over and over again, or you just take one group of data and you analyze it in many different ways until suddenly you get what looks like a statistically unlikely result, and now it's publishable. I think that this was a bigger problem earlier. I think that people in the last couple decades have caught on to the dangers of this and are very concerned about it, even in the social sciences. I mean, a lot of issues, a lot of famous results in psychology, for example, have been shown to be non-replicable. They were there in the first study, but they're not there when you look for them again. And I think that it's healthy that those fields are undergoing that investigation of previous results. It's less of a worry in physics, again, because physics is easy. It's easy to collect an enormous amount of data. In particle physics, you don't say you discovered a new particle really until you have 5 standard deviations of statistical significance. There will never be a psychology experiment that gets 5 sigma of statistical significance. There's just too much noise in human beings, and there's only so many human beings you can do the experiment on. So you wouldn't have a field of psychology if you demanded that all the results had to have 5 sigma statistical significance. Furthermore, since you have so much data in particle physics, for example, you can be very, very careful about what in that field, in the particle physics field, it's called the look elsewhere effect. When you measure the Higgs boson, for example, and you say, what is the statistical significance of the fact that at this particular part of the plot, I have an excess of events? That's what it looks like when you have a Higgs boson signal from colliding protons together and looking for certain events, let's say with 2 energetic photons coming out. There's more energetic photons coming out with a certain energy than with other energies. That's the signal that you made a Higgs boson along the way. But there's 2 very different questions you can ask. One question is, what is the statistical significance of, or the statistical likelihood of this kind of fluctuation at this particular point? Versus, in other words, at this particular energy in the total energy spectrum versus somewhere in the energy spectrum getting a fluctuation that big. It's much more likely that somewhere you'll get one than you'll get it in any particular place. So just the fact that you found it in a particular place doesn't mean you can say, well, I'm just going to calculate the statistical significance of having this particular anomaly, because there are a lot of other anomalies you could have had and those would have counted too, and that makes it easier to find an anomaly. So I don't think that particle physics, for example, or other large data set fields where you have enough data to be careful about this are really in danger here. In general, also, I want to say that it's not that modern scientific culture somewhat incentivizes false positives. Life incentivizes false positives. Of course, you want to say that whatever you're doing is interesting and important, right? And you want to kind of push things that seem to be going well. That is just human nature. Certainly there was no shortage of this kind of thing in non-modern scientific culture. We all know the story of looking for Vulcan, the planet that was supposed to be inside Mercury, and in an orbit closer to the sun than Mercury's orbit, that was supposed to explain the discrepancy between the prediction of Mercury's precession and its actual value. People found it. People predicted the planet and they found it in the data because they wanted to find it. It wasn't really there. They were fooling themselves because there's an incentive for false positives. So I think that, like I said before, eventually science catches up. It can take time, and you should always be very, very careful, very, very on the lookout for things like this. But eventually the data do tell you whether you're right or wrong. David Sotolongo says the wealth gap in the U.S. has been growing rapidly in recent decades, such that the top 0.1% are thought to have as much wealth as the bottom 90%. On top of that, we seem likely to have our first trillionaire within a few years. I'm curious about what, if anything, you think should be done about such wealth inequality and why. In particular, I wonder whether you think there should be any upper limit to how much wealth an individual can accumulate, such as in proportion to the wealth of the median citizen. So I think it's true that wealth inequality has been growing. I actually did, 1 minute worth of research. I never do research for AMA questions, but I did just want a reality check there because, again, there's incentives for false positives, right? People want to get statistics that prove the point they're trying to make. And in something like the economy, there's just so many different ways you can try to measure something like equality or inequality that you can cherry pick statistics to show what you want. So I just did a sort of unbiased search of whatever data were out there. I found a report from Oxfam saying that between 1989 and 2022, the top 0.1% U.S. household gained $39.5 million. The bottom 20% household gained less than $8,500. So basically, the rate of wealth accumulation in the top 1% is the top 1 or 0.1% is much, much faster. Oh, yeah. So the top 0.1% gained about 40 million. The top 1% gained about 8 million. So even the difference between the 1% and the 0.1% is very big. And there's another article from Chicago Booth Review of Business, I guess, that says the income share of the top 0.01% rose from about 2.5% to about 5% between 1995 and 2015. So 5% is not large, but it doubled in 20 years, which is saying something. So I think it's real. I think the effect is real. Wealth inequality is growing here in the U.S. Is it a problem? I think it is a problem, not because I think that morally it's wrong to have such wealth inequalities. Maybe you could make that argument, but I don't think that's the most important factor in my mind. I think it leads to bad outcomes in what you hope is a democracy. I care less about the fact that someone can buy a yacht than the effect that someone can buy an election, right? By just pouring a huge amount of money. It's certainly not foolproof. We've seen plenty of examples of people pouring huge amounts of money into elections without winning them, but it distorts the conversation when the voice of someone who just happens to have a lot of money is so much bigger, so much louder, so much more noticeable than the voice of someone who doesn't. That's very hard to justify morally. And you see it in quotes from various politicians who quotes from various wealthy people who, when a new politician gets elected, they're mad at them because they're like, well, I tried to get a meeting with this guy. He wouldn't take a meeting with me. And, someone who is at poverty level would never say that. Like, I tried to make a meeting with this guy and he wouldn't get a meeting with me. But the expectation is if you have a lot of money, you should have a bigger voice, which I do think raises problems because I think that systematically the set of wealthy people are not necessarily going to have the same goals and policy preferences that the country as a whole is going to have. So, but I don't think we need drastic, everyone knows how to fix this. This is not like a hard problem, okay? This is a problem of whether you want to do it or not. We just have taxes. Taxes are what do it. You can argue about what taxes are the best, whether it should be income taxes or wealth taxes or inheritance taxes or capital gains taxes. Those are all perfectly good policy debates to have. But if you don't want huge wealth inequality, or if you don't want wealth inequality to grow, then you should have higher taxes. Everyone knows this. This is not something that I really think should be controversial. I think once you start talking about ideas like an upper limit to how much wealth an individual can accumulate, all sorts of unanticipated bad things could happen. People could start trying to game the system, of course, which I know they already do, but there'd be new ways to game the system. Who knows how to count what counts as wealth and things like that, and it would just rub some people the wrong way and therefore be politically unpopular. Why bother with all these difficult attempts to do things in weird and creative ways when we know exactly how to fix the problem? We're just choosing not to. Ken Wolf says, in a local by-election, I was one of 15% of registered voters who bothered to cast a ballot. From my perspective, annoyingly, the candidate who wants to reduce residential road speed limits in a neighborhood entirely unsuited for that measure won. Should I be charitable and acknowledge that people have jobs and families and other things to deal with, or is it okay to be annoyed that a minority is in a position to impose their will on a majority that does not agree but did not even bother to show up? Well, I'm not sure that you should be annoyed at the minority. I think you could be annoyed at the majority that couldn't be bothered to show up. That's perfectly legit, I think. But, what are we going to do about it? I think that the actual thing to do about it is just to make voting and to be slightly knowledgeable, slightly informed about the choices of the vote, make that much, much easier. We really don't. I bet a lot of people didn't even know there was some by-election in your neighborhood. Mandatory voting is something that some countries try. I'm not necessarily in favor of that. I think that if someone doesn't care, they should be allowed to just not have an opinion and not vote. I don't see anything wrong with that. But I want to make it easier to care, to vote. I want to make it easier to vote, to know that there's a vote, know what the different options are. Again, I don't think that this is hard to do. It's just hard to make progress on doing sensible things in the messed up political environment we have right now. Zach McKinney talks about episode 330 with Peter Tornberg and says, given the robustness of polarizing social dynamics such as echo chambers and power law dynamics of attention when simulated using LLMs, as well as the attention and advertising-driven incentives at the heart of social media's business model, can you think of any shifts in human cultural attitudes or behaviors that once they reach a certain critical mass, you hypothesize could attenuate the polarizing dynamics of our culture and politics, including but not limited to social media? Well, I agree that these are problems. I think that I am not that on board with the phrase shifts in human cultural attitudes or behaviors. I think this is sort of putting the problem or the diagnosis in the wrong place. And I think I'm pretty consistent about this sort of attitude in general, that if there's some problem that is society-wide or whatever, that I'm generally not in favor of solutions to the problem that require changing the individual nature of the individual human beings in that society, or changing their behavior patterns, or changing their goals, or whatever. I just don't think that that's the way to actually get things done, or to get things changed in a society that is as large as ours and diverse as ours. I think you need to change the institutions and you need to change the incentives so that the people who still just do what they want to do are behaving better. We talked a little bit, I think we talked in the last AMA about sports betting and how it's kind of, maybe I just talked about this in my mind. I forget what I've talked about in real life or on the AMA. But sports betting is very common now, and it's just terrible for people in all sorts of different ways. It's ruining lives. It's ruining the sports because people are betting on things, and of course the actual athletes are therefore incentivized to do things they wouldn't otherwise do in the game because they can be part of a fix or something like that. And I don't think there's anything morally wrong with betting. I'm in favor of betting, that's fine, but I think we need far more guardrails, and restrictions on people's ability to do this. Like, I don't know, the maximum bet is $200 or something like that, right? Something that is not going to incentivize anyone to break the law in some dramatic way just to make $200. But right now you can make a lot of money, and the leagues themselves push it, and people lose their retirement funds or whatever, or go into debt, and it's a real problem. So I think that the thing is to not to, hector people into changing their attitudes so that they don't bet. It's to change the rules so that they can't bet in deleterious ways. And I know you're asking about social media, but I think the same thing is true. I think you got to change social media, and you got to change the reward structures and the business models and things like that, so that you don't get these bad effects of extremists being the intention mongers on social media and driving polarization and things like that. I think I don't know how to do that. That's not an easy problem. Okay, I admit the difficulty of that one, but I think that's the sort of direction in which we should be looking. Paul Turek says, last time, Anthony Rubo asked if you believe emergence arises ultimately from a fundamental, or if it is emergence all the way down. And it seemed clear that he meant all the way down the size scale, and you followed him there, so to speak. But according to Mad Dog Everettianism, the fundamental is the universe as described by its wave function, right? In which case, the fundamental is all the way up the size scale, or whatever one says when size scale is itself an emergent feature. And if that's right, can we poor listeners get more clarification when using these up and down metaphors? Sure, this is a very good question, and I was probably speaking sloppily, but this is actually a point that I often make myself. In many discussions of emergence, it is taken for granted that not only is there a microscopic level, if you want to call it that, or a lower level, and a macroscopic level, but that the macroscopic entities are literally made up of many little microscopic entities. And you're completely correct that this is not necessarily a part of our understanding of emergence. One of the examples that we use in the paper I wrote with Achuth Parola is classical mechanics emerging from quantum mechanics. A classical particle is point-like, right? It literally has zero size, whereas a quantum wave function has a spread via the uncertainty principle. So the entities in the classical description are literally universally smaller than the entities in the quantum description, and yet that is still emergence. There's absolutely no understanding or reason to think that what we call the lower level necessarily has to be associated with smaller physical sizes. What it has to be associated with is a more comprehensive, fine-grained description. The thing about a quantum state versus a classical particle is there are many quantum states that correspond to the same position of momentum for a classical particle. If you just take the expectation value of position of momentum in some quantum state, you get 6 numbers in 3 dimensions, right? 3 numbers for position, 3 numbers for momentum. But the quantum state you started with has an infinite number of numbers. It has psi of x for every x. So yeah, you're completely correct that the association with size is unnecessary. Nevertheless, people are going to use upper and lower, or higher and lower, or up and down as the way of talking about emergent levels and more fundamental levels. So that's just a linguistic choice. There's no reason to take that as supposed to be literally up or down. It's just that we've chosen to draw our levels with emergent levels at the top of the graph and more fundamental levels at the bottom of the graph. And I think that's fine. Rue Phillips says, in your recent solo episode on fine-tuning, you talked about God as a hypothesis worthy of being taken seriously. Can you elaborate a bit more on what the prerequisites would be to analyze this scientifically? For example, how well-defined does God have to be? How complete does your theory of how a universe would look under the God hypothesis have to be? And so on. I imagine this type of definition would apply to any universe origin hypothesis, but just trying to understand a bit more about how you would need it to be framed to take it seriously. Sure, this is a great question, but I do think that one has to distinguish between a hypothesis that is worthy of being taken seriously versus a hypothesis that one should attach a lot of credence to. Being taken seriously just means being allowed into the conversation, right? It doesn't actually mean that I should put a lot of credence in it, because I don't, in this case, put a lot of credence in it. But being well-defined is absolutely something that increases one's credence in a theory, but it's true all the time, not just with God, that we have credences in theories that are not fully well-defined, We don't understand quantum gravity completely, or we don't even know what string theory says, but, Joe Polchinski wrote a paper called What is String Theory? And he wrote it in, the mid-1990s, okay, long after people have been doing string theory for a long time, because parts of it are well-defined and parts of it are not. And that's okay, right? If you say, I'm debating between whether or not it's modified gravity versus dark matter. Well, there's a lot of specifics that you could have in a theory of dark matter, a lot of specifics you could have in a theory of modified gravity, but it's still okay to talk about the big baskets of theories, all of the dark matter theories versus all of the modified gravity theories. So even without a perfectly well-defined notion of God, one can still talk about theism as a general option, and one can assign credences to it, etc. I think it's perfectly legitimate to say that one's credence in that hypothesis should be low because the individual theories are not well-defined. I've made that point many, many times myself. But just the fact that we human beings have not defined the theory well enough is not enough to say that we should not include it in our list of possibilities. It was a theory that people took very, very seriously for thousands of years. I think that we know better now, but there's no a priori knowledge that the world is purely natural, right? We came to that by taking the different theories seriously. It's a sliding scale. There's not like a yes or no set of criteria. Here's what you need to have your theory be taken seriously. Some theories are more well-defined and taken more seriously, and other theories are less so, and that's fine. Jake Turin says, you often refer to the Boltzmann brain problem, but I think I think I understand the Boltzmann brain concept, but I'm unsure as to why it's a problem. I can understand that the idea that I am only a Boltzmann brain and my perceptions of the external universe are illusory is perhaps discomforting, but that's an aesthetic problem, not a physics or philosophy problem. Alternatively, maybe the Boltzmann brain concept is a problem not because it's impossible or illogical, but because it's simply a dead end, unprovable and undisprovable. Am I missing something? So yes, you're missing something. Look, first, just be super duper clear, nobody is arguing that you probably are a Boltzmann brain. No one thinks that, okay? It's a reductio. It is an argument that says, okay, if you believe this concept and this concept and this concept, then you end up saying that people like you typically would be Boltzmann brains, and that's bad. So that's where the problem comes from, because ultimately we want to reject cosmological models in which people like you typically are Boltzmann brains. And the reason, as I've talked about before, and I encourage you to read my paper called Why Boltzmann Brains Are Bad, it exactly explains this, it's right there in the title, is cognitive instability, which is the following idea, that if you decide that you probably are a Boltzmann brain, why did you decide that? Well, it's because you took some data about the world and you invented some rules of physics and mathematics and logic, and you used reason to decide that the best fit cosmological model is one in which a person like you is, with overwhelming probability, a Boltzmann brain or a Boltzmann fluctuation more broadly. There's no reason really to think that you're a disembodied brain out there. You could be a person in a room, but still all of that has fluctuated into existence rather than thermodynamically evolving in a sensible way after a Big Bang, okay? So the fact is that if you conclude that you probably did fluctuate into existence rather than sensibly thermodynamically evolving, then all of the ingredients that went into your conclusion also randomly fluctuated into existence. So all of your opinions about physics, about logic, about mathematics, about the evidence you have about the world, none of that is in any way reliable. It just randomly fluctuated into your brain. Therefore, you have zero reason to accept the conclusion that you reached by its own internal logic. That's what it means to be cognitively unstable. You cannot both believe it and think you have good reasons to believe it at the same time. So in my mind, the clear and easy and obvious thing to do is just to look for scenarios in which you are not a fluctuation out of higher entropy equilibrium. You did, in fact, evolve in exactly the way we think that you evolved, from a low entropy Big Bang initial condition. Kunal Menda says, even though there is now consensus that 3I Atlas is natural, did you agree with Avi Loeb's claim when he said it that there was a 30 to 40% chance of it being alien tech? No, certainly not. So for those of you who don't know, 3I Atlas is an interstellar comet that is traveling through the solar system right now. It is 100% clearly a comet. There's no real worry about it being anything else. But Avi Loeb, former Mindscape guest, sadly has just, I think, become less and less reasonable about these things over time. And he, in speaking of biases and false positives and so forth, claims everything in the world is an alien artifact, or at least has a large probability of being an alien artifact. The truth is, I mean, look, imagine taking it seriously that there's a 30 to 40% chance of it being alien technology. We think that under ordinary astrophysical circumstances, comets or asteroids or rocks from interstellar space should travel through the solar system all the time. And so the idea that this one, which acts exactly like a comet should act, has a 30% chance of being alien technology, would only make sense if you think that there's roughly the same order of magnitude of alien spaceships as there are comets going around, which requires a huge number of wandering alien spaceships. Look, be a good Bayesian about it. Would you expect that if there were an alien spaceship flying through the solar system, that it would just happen to look exactly like a comet? I think it would look very different. I think we would know right away, once we detected it, that it was not a comet at all. I think that applies to this case very clearly. Okay, I'm going to group a few questions together here. Krzysztof Radomski says, should the hypothesis that does not meet the scientific consensus be conveyed to the public as a scientific hypothesis? Or if so, because of freedom of speech, etc., to what extent? What led me to ask this question is a very annoying habit of bookstore staff locating books by Michael Behe and friends that question evolution in favor of creationism on the same shelf as real biology books are located. I only feel an urge to relocate them to the religion shelf. Jared says, I enjoyed your recent presentation with Gordon Pennycook on pseudo-profound bullshit. I say that I am in Gordon's risk category because I love being awed by new profound knowledge. For the technical subjects like physics, how does a layman spot bullshit if they don't have the expertise needed to properly consider the information? Should we rely on the speaker's reputation and how much they deviate from consensus? Randall Davis says, as someone with no academic background or college credits, how can I improve my ability to identify legitimate studies and results? I like to research many topics, including physics, but I'm curious if there are any methods or shortcuts to understanding study results and whether a study is likely to be well thought out and or likely to be correct. So all these questions are connected by the idea of how do we know if something out there that looks sort of dressed up like a reputable scientific claim really is reputable, or whether it's just pseudo-profound bullshit. There's no algorithm for doing this, right? This is hard. And of course, Christoph is also asking, should we even let people be exposed to the stuff that is not very legitimate? I mean, yes, we should let people be exposed to the stuff that is not very legitimate. For one thing, you know, the idea of speculating about beyond what we already know is at the heart of the scientific enterprise. I'm a believer that the single biggest thing we could do to improve science education is put more emphasis on the process by which science happens, rather than just on the results that we get. If people understood the nature of trial and error and hypothesis testing and Bayesian updating and all that stuff, they would be much better at judging what is worthwhile and what is not. And that means we have to let them in on the things that we ourselves still think are speculative hypotheses. I mean, I would be in big trouble if I didn't think that I was allowed to write about other things other than the scientific consensus. You know, in the biggest ideas in the universe books, I am just writing about scientific consensus, but in other books, I'm happy to speculate to my heart's content. We do need a toolkit, but it's not algorithmic. Like I said, you need to have certain warning signs that something is not completely kosher. I mean, look, usually you do. Usually it's not that hard to tell when something is not the scientific consensus, when something is being pushed from a certain angle, whether the person is not completely mainstream or what have you. Very often they will proudly proclaim that they are not mainstream, right? That it's perfectly obvious that this is not the establishment view. And of course, you don't have to believe the establishment view. There's no reason to do that. But as mentioned before, in terms of your own credences, if you are not an expert on something, then the establishment view is what you should take as the most likely thing. You don't have to believe it at 100%. But if the smartest people in the world who work on this thing for a living and are experts in it mostly believe something, you should tentatively place a lot of credence on that. So you can look to see where people are. You know, I remember when I watched, a friend of mine forced me to watch, what was the movie called? What the Bleep Do We Know? This was a nonsense movie about how quantum mechanics says you can create the world with your mind, right? And, you know, you just have to be careful. Like, there was a person on there, and my friend said, well, look, he's a professor at UCLA. And I said, well, no, if you look at what they actually say, he went to school at UCLA. He was an undergraduate at UCLA. Those are not exactly the same thing, right? If you're really curious, if something is really getting to you, go to Google Scholar. See if this person who is making some incredible claim really is reputable or not. You know, do they have a lot of papers? Do they have a lot of citations? Are they active in the field? Are they really writing cutting edge things, or are they just out on their own little island somewhere? In terms of legitimate studies and results, you know, if you read something online, it's becoming harder and harder to know the difference between a legitimate story about something worth paying attention to versus something that is either completely fabricated or something that is at least very, very speculative and doesn't yet quite deserve a lot of attention. But there are certain things you can look for. For one thing, you should have trusted sources, right? You should be able to know that if an article appears in a certain place, it's more likely to be carefully reported and fact-checked versus if an article appears in other places. Like, don't tell me that just because you see see something on Facebook, you're thinking that maybe there's some credibility there. When you're reading the articles, again, in the modern economy, where we have a lot of enshittification of things, a lot of things that look like articles about science are really just press releases and have very low credibility unless the person the press release is from is independently known to be very credible. How do you know the difference? The obvious thing to look for is in the article, are there people who are not involved with the study being quoted? Are there potentially skeptical voices being reached out to? A good science reporter, as I know because I'm married to one, doesn't just take the press release and rewrite it and then print it. You go out and do some reporting. You talk to experts. You ask, is this interesting or not? Is this worth following? And for a lot of good science outlets, and for a lot of good podcasts, for that matter, there's a lot of things one could talk about and which one just doesn't think are worth talking about. So sometimes if you only see certain things being mentioned in certain less reputable corners of the internet and you don't see them getting mentioned in the more reputable corners, you can maybe draw the conclusion that this is not quite as good. So I don't know if this is, things like that. I think it's mostly common sense, honestly. I don't think there's any expert level knowledge you need to know that something is a little bit sketchier, especially because, as we were talking about before, everyone has their biases. Everyone has their motivated reasoning, their wishful thinking, as Gordon Pennycook says, their unmotivated reasoning or their unmotivated unreasoning, unthinkingness. And you got to warn yourself against that. You have to be prepared to say, I really want this to be true. This sounds really cool. Therefore, I'm going to pretend that it's credible. And the world doesn't work like that. We have to protect ourselves before we worry about protecting anybody else. Gerard Sage says, over the years I've fallen in love with complexity theory and complexity science, and I'm interested in paths to pursue it academically. It just seems to be the discipline that works the way my brain works. I watch the Complexity Explorer lecture courses, I have the David Krakauer anthologies on the important papers, but I have no clue how to get into this subject in a professional academic capacity. What can I do in order to get into this discipline in a serious way? If it helps, I have a master's degree in chemistry and I'm looking at options for PhDs in various fields. Well, this is a great question. One could ask the same set of questions about natural philosophy or the foundations of physics. These are all areas that are perfectly well-defined and perfectly sensible areas to work in, but the academic pathways are less than perfectly obvious. There's not a lot of departments of philosophy of science. Like there's a department of philosophy, department of physics, but it's a very, very different experience if you go into one or the other. And so sadly, you just have to make that choice. Complexity is the same way. There are very, very few complexity science PhD programs. I'm assuming that if you say you want to get into something academically, that means you want to get a PhD and become a professor or a professional researcher of some sort. And that means getting a PhD. So we need a department in which to get a PhD. But there are very few, maybe like Northeastern has one. I'm not sure. They have a pretty active center for complexity. You can Google around, is there a center for complexity at a university, and look for that. But much more likely, what you should do is not actually say, I want to get a PhD in complexity, but say, I want to get a PhD in a certain recognized academic discipline, but within that discipline, I want to think about aspects of complexity. Maybe that discipline is chemistry. Maybe it is applied math. Maybe it's physics. Maybe it's economics. Maybe there's a lot of different things, linguistics, sociology, political science, all of these, computer science, all of these have their complexity science aspects to them. And when you're looking at PhD programs, you don't just sort of look at which ones are top ranked or something like that. You look at a very fine-grained level at who is working there, who are the professors, who are the potential advisors who could be your mentor in doing something like this. So I would say literally go down to the level of who is writing papers right now that you find interesting. Go in the archive or go on Google Scholar and look for papers with titles that you like. Look what departments they're in. Look at what universities they're in. Are they still active? Are they writing papers? Do they have graduate student co-authors on their papers? All of these questions. Don't think about, I'm a complexity scientist, but think about, I'm going to do a certain kind of research for my PhD, which will lead me to become educated and active in thinking about complexity. I think that's the way to do it. Kevin D. said, somebody told me the inverse square law is proof that we live in 3 dimensions. Can you explain why this is true? Why isn't it 1 over r cubed for 3 dimensions? I hope we really don't need too much proof that we live in 3 dimensions, at least macroscopically. I think that there's easier ways to prove it than the inverse square law. But your somebody is correct. The inverse square law for both electromagnetism, which is Coulomb's law, and for gravity, which is Newton's law of gravity, are related to the fact that we live in 3 spatial dimensions. In particular, if we lived in 4 spatial dimensions and otherwise gravity and electromagnetism were the same, we would once again have an r 1 over r to the cubed law. And the reason why, I've talked about this in many books if you're interested. I certainly talk about it in Space, Time, and Motion, Volume 1 of The Biggest Ideas. Think about it in terms of lines of force. It's not the only way to think about it, but it's a good way to think about it. If you have a line of force, gravitational force, what does that mean? It's the sort of imaginary line in space where if you have a collection of particles that are charged under that thing, so electrical charge or mass for gravity, they would all be pulled along that line toward the thing that is pulling them. So for either gravity or electromagnetism, for a charge or for a massive object, the lines of force radiate radially away from the object, from the source, and they never end. They don't end at least until they hit another object or something like that. So that's in contrast to the nuclear forces, which are short range. The strong nuclear force, the lines of force exist, but they don't radiate outward because they get tangled all up in each other because the gluons that carry them interact with each other. And the weak nuclear force, the lines of force radiate out, but they do end. They fade away because they're absorbed by the Higgs field that is surrounding them. But for electricity, for the electromagnetic force, and for gravity, they just go on forever. But what happens is they get more and more dilute, these lines of force, right? If there's a high density, the density is a continuum, so it's infinite, but you can still talk about the relative density of these imaginary lines of force, and they get spread out. How do they get spread out? They get spread out on a sphere of a fixed distance away from the source. So if you think about 2 dimensions, to make things very, very easy, if I put a dot on a 2-dimensional plane and I draw a circle a certain distance around it, the plane is 2-dimensional, but the circle is 1-dimensional. And so as I double the radius of the circle, I double the length of the circle, right? Whereas in 3 dimensions of space, so I put a dot there and I draw a line of constant distance from it, that's a sphere, a 2-dimensional sphere in 3 dimensions. If I double the radius, the area goes up by a factor of 4. It goes up as the radius squared because it's 2-dimensional. That's the inverse square law, because the lines of force, there's a constant number of them, getting further and further apart, further and further diluted, and the dilution goes as the area of the sphere that they're passing through, and that area goes as the radius squared, so the dilution is 1 over r squared, and that's the inverse square law. Now I'm going to group a bunch of questions together. They might not be superficially the same, but there's an underlying similarity there. Red Antonov says, in the episode with David Tong, you discussed fermion doubling in lattice gauge theories as a consequence of the Ninomiya theorem. Sorry, I don't pronounce these. I read these words in my professional capacity, but I don't ever pronounce them out loud. Would right-handed neutrinos then be present in all simulations of the universe unless the designers did extra work to write codes that hide them? Kurt Stahl says, I just read an article. See, you thought that was going to be about quantum field theory. It's actually about simulation hypothesis. Kurt Stahl says, I just read an article that claims that the universe is being a simulation has been ruled out. The article I read was pretty high level, though it did reference Gödel, Tarski, and Chaitin, so I presume it has some chance of being valid. My question is, what impact this, assuming it holds, has on works such as Wolfram's attempt to use cellular automata and other physics-related issues? And finally, David Wright says, are there entities such as vacuum energy or the quantum foam that are necessary prerequisites for the existence of any universe? Do these always exist and can never not exist? Is this set of necessary entities an ontological God? So, 3 very different seeming questions. Red is talking about putting fermions on a lattice and its implications for the simulation hypothesis. Kurt is talking about, is the simulation hypothesis ruled out by data? And David is saying, are there necessary entities that qualify as an ontological God? The answer to all these questions is you got to be way more imaginative and open-minded about what the laws of physics might look like in the land of the simulators, if you think that there could be a simulation hypothesis. Or just more generally for David's question, in any universe, if you say, are there entities such as vacuum energy or the quantum foam that are necessary prerequisites to the existence of any universe? No, not at all. There's all sorts of potential universes that I can imagine. I can imagine a universe that is just a point, right? I can absolutely imagine universes without vacuum energy, or I can imagine universes without quantum mechanics, much less quantum foam. There's a lot of universes you can imagine. I can imagine universes without right-handed neutrinos. I can imagine universes without quantum field theory. In particular, for the quantum field theory question, the problem with the right-handed neutrinos, or the problem with fermion doubling, I should say, is that there's a specific way of trying to regularize quantum field theories by putting them on a lattice that runs into this problem with doubling the number of fermions. But that's not necessarily the only way to do quantum field theory or to define it, have a lattice in space. Certainly the simulators who are simulating our entire universe might be way more clever than that. They might even just have a continuum, right? They might not have a lattice at all. Who knows what they could do? They might be, from our perspective, essentially infinitely powerful. So I don't think that there's any thing that we can draw, any conclusions we can draw from our struggles about what the struggles of the simulators might be. For Kurt's question, has someone ruled out the simulation hypothesis? Well, first let me note that referencing Gödel, Tarski, Chaitin is actually not evidence that the thing you're reading has a chance of being valid. Indeed, that kind of sounds like a little bit of name dropping, right? I mean, these are famous names that someone can mention without actually having read their papers very carefully. It's more, if we're talking about evidence that something is respectable, it's better if people are referencing things that are appearing in the research literature that you and I have never heard of, because they're actually relevant to what they're writing about. If they're only citing things that have appeared in the popular discussion of things, that's a red flag. But anyway, you can't rule out the simulation hypothesis because, again, who knows how powerful the simulators could be? What you can do, and what I presume the study you're talking about did, although I'm not familiar with it, is make an assumption and say, if the simulation has such and such properties, then we would observe this and we don't. That's perfectly okay as long as you're very clear that you're ruling out a certain variety of the simulation hypothesis. It's much like, God, right? You can rule out certain conceptions of God, but until someone tells you exactly what they mean by God, you can't just rule out God. You can find the concept unnecessary in a way that goes back to our friend Pierre-Simon Laplace, but you can't just rule it out by saying, I know for a fact that if God existed, the universe would be a certain way. As to what it all means for things like Wolfram's attempt using cellular automata, I have no idea, because I have no idea what the predictions of that theory are. I mean, we had Stephen Wolfram on the podcast, and I talked with him, and I said, does your theory make predictions that deviate from standard quantum mechanics? And his answer was maybe. He doesn't even know for sure, right? So what can I say about whether or not any particular experimental result is relevant here? I don't want to denigrate the effort. I think it's very, very important to make these efforts to think big and try to come up with new ways of thinking about the universe. But like we said before, often theories are not very well defined, and nevertheless, you have to have a credence in them and go forward, and that's how life works, whether we like it or not. Will Robinson says, you mentioned the possibility of a cosmological multiverse where regions very far away from each other could have different values of fundamental constants, different laws of physics, perhaps even different numbers of macroscopic dimensions. Do the formulations of this theory indicate what would be happening at the boundary between such regions? Years of listening to Mindscape has made me compulsively try to understand boundary conditions. Sure. I think that any good theory, any well-defined theory, would indicate what is happening at the boundary between such regions. There are different ways to get a cosmological multiverse, and so there's not a one unique answer. The most common way is something called eternal inflation. Inflationary cosmology posits the existence of some new scalar field, the inflaton field, which drives inflation, and then under very reasonable criteria for the potential energy of that field, eternal inflation can go on forever. Inflation, I should say, can go on forever. It could be eternal. In some regions of the universe, it will stop, but in some other regions, inflation keeps going, and the fact that it keeps going there means that that region of space grows faster and comes to dominate the cubic centimeter volume of the universe, right? So what is the boundary in between the regions? It's the area where the inflaton field is halfway in between, inflating and not inflating, which is, it doesn't want to be there, right? Like the inflaton field likes being in the inflationary region because that's there's some friction there and it keeps the universe inflating, or it likes sitting at the bottom of its potential, but it needs to pass through from one value to the other in order for inflation to end somewhere. In conventional ways of talking about inflation, that ending happens as a function of time, right? You say, well, here's the inflaton, it rolls down the hill of its scalar field potential and it gets to the bottom. All you have to do is thinking of that happening differently in different regions of space. So in one region of space, it rolls down the hill, in the other region it doesn't. In between, it will interpolate between there and there. It's going to depend on details of the potential, but the interpolating region could be very broad or it could be very narrow. It could look essentially like a wall, right? That it's very clear that on one side you've stopped inflating, on the other side it keeps going. This is basically a version of a domain wall. It's not exactly the same because usually the domain walls we talk about are have the same energy inside and out, and this doesn't. So sometimes these are called bubble walls. Bubbles of true vacuum and false vacuum, and they have dynamics, and they can move at different rates of speed, and people talk about them. People study them. People write papers about them. Now, like I said, we can also have a sort of more smushy kind of situation where the variation of the value of the field is more gradual, and there, you might live in the region, which is between, on the one side, inflation's still going on the other side, it has ended. But this is going to all depend on details. I think the relevant answer here is yes, within some specific well-defined theory of how the multiverse comes about, we can talk very specifically about what the boundary between regions looks like. I'm going to group two more questions together. Yusef says, I was rewatching your episode with Kip Thorne, and it was mentioned that black holes are not things of matter, but curvatures in space-time. So my question is, where does the mass go? Is it even worthwhile to ask this question since we can describe the macroscopic behavior of black holes as curvature in spacetime? I ask because some black holes start off as objects that contain matter, so going from something that has matter to curvature in spacetime is a tough idea to wrap my head around. And then Perry Juan says, the internet told me that black holes become less dense the bigger they get. I don't believe I've heard you on this subject. Would you mind teasing out the subtlety? Does this have broader implications? Yeah, so both of these questions are about what the interiors of black holes look like and where does the mass go and how big is it and things like that. So the mass doesn't go anywhere when you make a black hole. What can I say? Talking about black holes is difficult because in general relativity, where space-time is curved, there's this truism that there's no unique way of dividing up space-time into space and time. Okay, that's always true, I should say. Even in special relativity, that's very true. But in special relativity, even though there's no unique way to do it, there's kind of a natural way to do it. So we think we know what we're talking about when we say this object, the car on the street here has a distance, a size at one moment of time. I could slice space-time in some weird way that would have a very different size, but there's no reason to do that, so we don't do it. In black holes, the situation is reversed. There's just no obvious way to do it. There's plenty of ways you can do it, and you can get very different answers. Carlo Rovelli, who's one of the first Mindscape guests, wrote a paper with Christodoulou a while back where they pointed out that there is, inside a black hole, there's what they call a maximal slicing, which is the biggest space-like surface that you can fit inside the black hole. And it is very, 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 very big, and it's growing with time, even though the black hole from the outside looks like it's more or less static with time. That's just because everything is weird in a black hole. What can I tell you? But what I can say is that if you make a black hole out of matter, if the matter collapses and makes a black hole, most of the interior of the black hole is empty, but not all of it. That matter is still there. It didn't go away. It's just that its gravitational field has created the curvature of space-time around it that creates an event horizon which separates the interior of the black hole from the exterior. So Kip is correct, and everyone is correct when they say don't think of a black hole as like an object, a sort of solid thing, right? It's mostly empty space. But the matter that went into it is still inside. It's just that its gravitational field has become very, very strong and noticeable. From the outside, it looks like a two-dimensional event horizon that separates the interior from the exterior. So you can't see the matter anymore. From the point of view of an external observer, it makes sense to think of it as a region of space. And who cares whether there's matter in there or not? What matters is the overall mass of the black hole. For Perry's question, yes, black holes become less dense the bigger they get. That's not that hard to see. The Schwarzschild radius of a black hole is proportional to its mass. So if you forgot that black holes have curved spacetime inside and instead pretended everything was flat spacetime, the interior of a sphere goes as its radius cubed, right? But the radius of a black hole just goes as the radius to the first power. It is the radius. And so if the radius is proportional to the mass of the black hole, the size of the black hole, if you think that it goes as the radius cubed, goes as the mass cubed. Okay, so the density is the mass divided by the radius. So that's mass divided by mass cubed, which is 1 over mass squared. And indeed, as the mass gets bigger, you get less dense. Now, that's a little bit of nonsense, as we just talked about, because the interior volume of a black hole is not the interior of flat spacetime, but also it's not well defined. So you can't even say what the density of a black hole truly is. So on the one hand, it's fair to say that black holes become less dense the bigger they get. On the other hand, it doesn't actually mean anything because there's no such thing as the density of a black hole. Bo Perizzo says, what do you think of the tactic of political influence employed by groups that openly adopt the principles of the opposition in an almost ironic performance, like the Satanic Temple? I think that's more about performance than about political influence. I don't think that the Satanic Temple, for example, has a lot of political influence. You know, I think, and maybe this is slightly cynical of me, but I think that as a matter of practical politics, there are many, many things that people do that are more about making them feel good and thinking that they're doing something than truly about making the world a better place. And I'm not trying to say that people who do ironic performances like this, such as those in the Satanic Temple, don't have a sincere belief that they're trying to make the world a better place and don't sincerely want the world to be a better place. Maybe they do, maybe they don't. I'm not that familiar, but that's fine. I just don't think that the tactic is very effective, but it sort of seems effective maybe to the people who are doing it. And maybe I'm completely wrong about that. I mean, this is absolutely one of those questions that you require data. You know, it's not really my thoughts or my feelings that are going to matter here. You should actually study it. And as we said before, studying things in the social sciences is way harder than studying them in physics or chemistry. James Allen says, outside of lab conditions and cats in boxes, how often do quantum events bubble up to have noticeable macroscopic consequences? If I'm in an ice cream shop undecided, could there be events in my brain that branch the wave function where I'm taking vanilla in half the branches and chocolate in the other? Or is it more like from the time I woke up that morning, the wave function is constantly branching, but I'm still having chocolate in all the branches where I don't encounter Boltzmann brain in my shower? I think this is a good question, and people ask it all the time, but I honestly just don't know the answer. There's two kinds of questions you're asking here. How often do quantum events bubble up to have noticeable macroscopic consequences? All the time. That happens very frequently. Every time you have a Geiger counter and it clicks, That click is a macroscopic consequence of an underlying quantum event, okay? When I wrote my book, Something Deeply Hidden, I ran a quantum random number generator, and the results of that number generator were put into the book. So there's a big macroscopic consequence of quantum events. You can buy the Universe Splitter app on your phone, and you can do things based on the Universe Splitter. And again, macroscopic consequences. But I think what you are asking is our everyday behavior, without trying to pay attention to quantum measurements, governed by quantum events in ways that quantum randomness feeds into macroscopic behavior. So I don't know the answer to that. I can see arguments for either side. On the one hand, you have the human brain is really not a quantum object. It's a pretty darn classical object. You know, the electric fields, the chemicals moving around, even though they're pretty small, are still big enough to be pretty darn classical. Okay, so that would be an argument, and decoherence happens very rapidly, et cetera, et cetera. The brain is a warm, wet thing that roughly talks, acts, moves dynamically in a classical way. I think that's one perfectly sensible attitude to have about this. The counter argument, which people like Andy Albrecht have explored, is, look, we do have things that are pretty small going on in our brain. This molecule sends a little electrochemical transmitter to that molecule. You could imagine there's a probability that is non-trivial for it to happen or not happen at the threshold. And there is a matter of thresholds being very important. Since we all now have neural networks, or we know about neural networks now, you may have heard that neurons in our brains are nonlinear. That is to say, they don't output a signal that is proportional to the input. If the neurons were linear, then on the one hand, there would not be any dramatic threshold effects. But on the other hand, maybe we wouldn't be so smart either. So basically, if you have exactly enough input, then the neuron fires. But if you have less than that, it doesn't fire at all. So it's a nonlinear effect in that way. The fact that there's that nonlinear effect, and the fact that there's something called chaotic dynamics, where small changes in initial conditions can grow to large macroscopic differences, opens the door for there to be dramatically non-trivial probability amplitudes for very different macroscopic behaviors based on things going on in our brain. Like I said, I doubt that that's actually very common, but it's conceivable to me, and it sounds like a hard math problem, that math/physics/chemistry problem that I haven't actually seen anyone tackle very carefully. Paul Hess says, does accepting Mond theories — Mond is the alternative to dark matter that changes either Newtonian dynamics or gravitational dynamics depending on how you want to cast the theory — does accepting Mond theories mean that we are rejecting the equivalence principle? If yes, does that make the various Mond solutions even less credible alternatives to dark matter? Well, I don't think so. I don't think that you need to reject the principle of equivalence, at least the weak principle of equivalence, to accept Mond, but that might actually depend on how you formulate it. But I can tell you, as an expert on the principle of equivalence, who cares if you violate the principle of equivalence? It's really actually not that sacred a physical principle. The equivalence principle was used by Einstein to invent general relativity. The equivalence principle, for those of you who don't know, the simple version is objects of different masses and compositions fall the same way in a gravitational field. So the reason it's called the equivalence principle is because everything falls the same way in a gravitational field. If you were in no gravitational field, but instead in an accelerating reference frame, like in a rocket ship or something like that, you would also see things fall all at the same rate. And so you can't tell the difference in a small region of space-time, whether you're in a gravitational field or just in an accelerating reference frame. That's the equivalence being talked about. And Einstein extended it from just dropping objects to any law of physics looks the same in an accelerating reference frame and in a gravitational field. So I don't see why it would be necessary to violate that in Mond, but also I can easily invent theories that violate it. And, it depends on what you mean by gravitational field and a whole bunch of different things. So if you had a theory that fit the data, violating the principle of equivalence would not bother you at all, I think. The problem with Mond is that it doesn't fit the data. It's ruled out by all sorts of different kinds of data, most obviously by the cosmic microwave background, but by other things as well. So it's already uncredible enough that I don't need to worry about it violating the principle of equivalence. Ophir Overbuch says, does our current understanding of quantum physics allow for the following science fiction story? In the far future, a giant empire controls all colonized planets in the galaxy, and it is oppressive. A resistance forms, and it wants to overthrow the empire, but it is crucial that the revolt will occur in multiple regions of the galaxy at once, and the revolutionaries in different regions will be coordinated in their attack. The leaders of the resistance come up with the following ingenious plan. They know they can't communicate fast across the galaxy, and that if they send regular signals, they are likely to get intercepted by the Empire, which will then reinforce their defenses on key targets. However, the resistance can send entangled particles from a central location to all the other locations. When the particles reach their destinations, they are being observed. Each observation orders the execution of a specific plan out of a pre-distributed bank of plans. This way, no one can control in advance which plan is to be executed, so no one can betray the cause, but whatever the measurement of the particle turns out to be, because the particles are entangled, it ends up being the same plan across the galaxy. So I will hopefully that was clear. Entangled particles very, very far away. I do an EPR kind of thing. I measure one, and now I know what everyone else is going to get, so I know which plans to execute. I will let everyone listening here try to think through for themselves whether they think that's a feasible plan. You can pause the podcast here if you want. The answer is no, it is not a feasible plan. I mean, you knew it was not a feasible plan because this is trying to sneak around the limits on faster-than-light communication, which quantum mechanics does not let you do. The problem is, there was a part of Ophir's question where if they send regular signals, they are likely to get intercepted by the Empire. Okay, but then later, each observation orders the execution of a specific plan out of a pre-distributed bank of plans. How are they able to pre-distribute the bank of plans if all of their signals are intercepted by the Empire? The point is that to do this coordination, you need to previously send classical signals across the galaxy. And so why not just send the plans if you can do that, right? Just send the plans and say, do this at a certain time. If you can send the list of options without it being intercepted, then you can just send the signal to do the plan without it being intercepted. So quantum entanglement does let you know what result other people are going to get from doing their measurements, but in no way does that help you coordinate activities that you couldn't have more easily done just regular classical methods. Calvin Firth says, from the Friedmann equation, the curvature of the universe can be related to its energy contents, omega k equals 1 minus omega naught. Is there a causal relationship between curvature and energy contents? Does one determine the other, or can we only say that they are related? This is a great question because, people see equations in physics and they talk about them in certain ways. We say that an electron has a charge and that charge causes an electric field around the electron. And we can relate them. There's Gauss's law. So if you integrate up the electric field around a sphere, around the electron, that's equal to the charge, okay? But could you equally well say that the electric field causes the charge? And the answer is yes, you could. And likewise, in the Friedmann equation, you relate the curvature of space to the amount of matter. Does one cause the other? Not in any way that we would ordinarily associate to the word cause. You have to be careful, because as frequently happens, you're using ordinary language to talk about something very precise and mathematical. And when you do that, sometimes the meaning of the ordinary language words doesn't map onto what you're trying to say quite as precisely as you might like. So it's never really right to say that one term in an equation causes another one in the usual way that you and I would use the word cause and effect. They're all bound up together, and I think that's the best way to think about it. In particular, in the Friedmann equation, there's no priority which one comes first, which one comes second. There's just what we call a constraint, that given these various quantities, some particular combination of them has to obey a certain relationship. In that kind of case, you don't pick out one to be determining all the others. Mikkel Benedson says, in your recent solo podcast on fine-tuning, you discussed dynamical dark energy. Later, when talking about the flatness problem, you referred to the inflaton field as a sort of dark energy. This made me wonder, could a time-varying cosmological constant explain both inflation and dark energy, i.e. the cosmological constant had an extremely high value right after the Big Bang, giving rise to a rapid expansion of the universe, inflation, and then quickly decayed to near zero, thus acting like the dark matter we see today. So on the one hand, roughly speaking, the answer is yes to your question, and people have absolutely looked into this scenario. Can the dark energy that is pushing our universe apart now and the dark energy that caused inflation be related to each other somehow? Yes, absolutely, it could. We don't know. We have no evidence that it's true, but yes, it could. But two things. One is, please do not call it a time-varying cosmological constant. It's really not that, right? Things that are constant don't just vary with time. You can have a field that varies with time that contributes to the apparent cosmological constant, and indeed that's what we do. We would call it the inflaton if it's causing inflation. We might call it quintessence or something like that if it's causing dark energy today. So you can ask, is the inflaton field the same as the quintessence field, or does it turn into it, or something like that? And that's the kind of thing you're absolutely allowed to ask. The other thing is that there's a good reason why a scenario like this is actually not easy to make it work. The energy scales of relevance to inflation and of relevance to dark energy are incredibly different from each other. So on the one hand, they both seem to involve acceleration of the universe and maybe a scalar field, but other than that, they have nothing to do with each other, right? So, of course, it's natural to ask whether they might have something to do with each other, but I think the smart money is that unless we have a good reason to think that, they're probably two different things. Martin Leitner says, as I understand it, cosmic expansion violates the conservation of energy by basically creating new energy from nothing, which is okay because conservation of energy only holds in a static universe. At the same time, photons traveling through an expanding universe lose energy, as seen in the redshift of the cosmic background radiation, to nowhere in particular. Do we know which effect is bigger? Could we describe the cosmic expansion as being driven by photons traveling through space, pushing it apart? So yeah, we know exactly what is going on here, and I think some of the ideas that you're talking about are more or less correct, but some of the words are not exactly straight on. Energy in an expanding universe is not uniquely defined, okay? So it depends on what you mean by energy when you say, is energy conserved or not? I think in the simplest definition of energy, which is to say there's an energy density through space, and I just take the sum of all the energy density in a volume and call that the energy, that quantity is not conserved as the universe expands. It would be conserved if the universe were not expanding. So that's why I think it's perfectly okay to say the expansion of the universe violates the conservation of energy. But it's not like all hell is broken loose. There is an equation. The equation used to say the change in the energy over time is zero. Now, the new equation in an expanding universe says the change in the energy of the universe over time is related in a very precise way to the expansion of the universe, okay? So what that precise way is depends on where the energy comes from. For photons, like you say, or radiation more generally, energy decreases as the universe expands. For dark energy or cosmological constant, the energy increases as the universe expands. It's not that it's creating new energy from nothing or disappearing energy from nothing. It's just that the rule for the total amount of energy is different in an expanding universe. And we know exactly how much it is. These two effects, the decrease in energy from photons and the increase from dark energy, have nothing to do with each other and are not related in any way. These days, for example, the total energy in radiation is very small, and the fact that it's getting smaller faster is irrelevant. It's just very, very small, much less than the energy in the dark energy, by a factor of, 10,000 or something like that. So two different effects, but we understand everything that's going on. There is an equation called the covariant energy conservation equation, which tells us exactly what's happening. Julian Voitel says, is everything entangled with everything else since there is only one wave function of the universe? Or are there separate non-entangled entities? Well, that depends on the wave function of the universe. So there is only one wave function, but some wave functions written as combinations of some subsystems of them are entangled, and some are not. That's what it is. So, depending on what the wave function of the universe actually is. It's a little bit more complicated by the fact that if you believe in many worlds, that there's a difference between whether or not two subsystems of the universe are entangled in the wave function of the universe as a whole versus if they're entangled on a particular branch of the wave function. On any one branch, it's easy to break entanglement and make something unentangled. All you have to do is measure it, or in particular, measure enough aspects of it that you get it to a unique quantum state. So if you have a simple harmonic oscillator, and it has completely unique quantum states, the lowest energy state, the first energy state, the second one, etc., and you start with your harmonic oscillator in a superposition of all those different energy states, and maybe it's entangled, right? Maybe it's entangled with a whole bunch of things in the rest of the world. That's fine. But now I measure its energy. I measure the energy of the harmonic oscillator, I get a result, and now I know, number one, exactly what the state of the harmonic oscillator is. It's that energy state. And number two, it's not entangled with anything else. I've broken the entanglement by doing that measurement. So, well, at least on the branch of the wave function where I am. On the other branches, if you combine everything together, there's still entanglement there. So there's no problem in general, in principle, with having unentangled parts of the universe. Ed Said Stuff says, does the existence of massless particles pose any kind of challenge to physicalism as it's generally understood? If something like a photon has no mass, no rest energy, no proper location, and can't even be said to exist at a single point in space-time, is it physical? How should I think of physicalism given the overall picture of what we currently know? Well, the fact that you're using the word physicalism is kind of a hint that everything is fine. In the past, you might have used the word materialism. There's the idea that what really existed is matter, or matter and energy in the universe, okay? But eventually we realized, that's a particular view on physics and the fundamental ontology of reality, and we don't know if that's the right view. Indeed, I would think that it's better to say that wave functions in Hilbert space are a better way, quantum vectors in Hilbert space are a better way of thinking about the fundamental ontology rather than matter distributed in space-time. But that's no challenge to physicalism whatsoever. Physicalism just means there's physical stuff. I don't know what it is. I don't care what it is, but it's the physical world as opposed to the non-physical world, whether the non-physical world is supernatural or whether it's just, mathematics or something like that. Physical stuff can be all sorts of different things, certainly including photons. I mean, photons having no mass, no location, etc., all that just comes out of electromagnetism. It really comes out of classical electromagnetism. Electromagnetic wave moves at the speed of light, has no proper location, all of those things. Does not exist at just one single point in space-time. But it would be weird to think that the electric or magnetic fields somehow offer a challenge to physicalism. Maxime B. says, have you considered that an open democratic society with a strong scientific culture might represent a critical point, like a phase transition between two extremes, authoritarian dictatorship or theocracy on one side and anarchy on the other? In this framework, useful information or signals can propagate effectively across society, creating long-range correlations while maintaining enough diversity and information content. Does your work on physics of democracy consider this aspect? Yeah, it absolutely does, and it absolutely can. I don't know exactly the detailed, I don't think it is known, the detailed relationship between words like open and democratic and strong scientific culture. But certainly there's different social organizations, generally speaking, that will have different hierarchical structures. Like one person is the boss of everybody, like you say, is one extreme, and nobody is the boss of anybody is another extreme. And a sort of shared, layered organization of society where there's a hierarchy where, there's one level, and then there's another level, and there's another level, and another level with distributions of authority and responsibility through nations, states, localities, organizations, and so forth, is an intermediate point between those two things. And so one wants to know where do those structures come from? Structures with that kind of hierarchical pattern exist all over nature. It's not just human-made things. So why do they exist? Where do they come from? What makes them stable? How can you make them more stable? These are all physics of democracy questions, very much. Yes, I'm not going to give you the answers because I don't know what they are. I don't think that physics of democracy as an idea really just gives you answers once and for all, so much as it suggests ways of thinking about these kinds of questions. Chris Kaltwasser says, I believe you've made it quite clear that you fully endorse the many worlds interpretation of quantum mechanics, while Roger Penrose has argued strongly against it, despite having once accepted it for about a year before deciding it just didn't add up. His later quantum consciousness ideas depend on objective collapse, which seems directly at odds with many worlds. Do you see any possible way that Penrose's objective collapse-based quantum consciousness could fit within a many worlds framework, or are the two views fundamentally irreconcilable? I think they're irreconcilable. Yeah, like the whole point of many worlds, again, it's not about the worlds. It's about the quantum state always obeying the Schrödinger equation. And so as soon as you say the phrase objective collapse, that means the wave function collapses in a way that does not obey the Schrödinger equation. So it's pretty much a very clear dichotomy. You obey the Schrödinger equation or you don't. Many worlds does, Penrose does not. Anonymous asks a priority question. I am currently trying to climb out of the depths of nihilism as I witness the entire concept of reasoning collapse around us all. I have recently discovered that a concept exists which gives me some hope for the future. Consequentialism. Has the U.S. right wing been doing a form of consequentialism this whole time? Is this why they appear to have won at this time? Do you understand what I'm getting at? Can you please help me trudge through this mire? I'm not sure I can help you trudge through this mire. I am familiar with the idea of consequentialism. I talk about it, for example, in my book, The Big Picture. It's a concept in moral philosophy. The general distinction is drawn between different sort of schools of thought about morality. What is it that matters? What is it that makes a certain action moral or not? And consequentialism is the idea that what makes a certain action moral or not is its consequences, the consequences of that action. This is as opposed to a deontological approach, which says that the morality or non-morality of the act inheres in the nature of the act itself, not in its consequences. So deontology is all about rules. Just if you obey the rules, then you're being moral. And consequentialism is, even if you obey the rules, if you do something you know is going to cause bad consequences, that's immoral. A traditional example is the trolley problem, which I'm pretty sure back when I wrote The Big Picture was not a very well-known thing, but nowadays everyone knows about the trolley problem. You have a choice. There's a trolley speeding toward 5 people tied to the track, and if you flip a switch, you can switch it onto another track and save those 5 people. The problem is you end up killing another person who is on the track that you switch it to. I don't know why you're hanging around at this place that has all these people tied to the tracks, but the deontologist might say, well, you shouldn't take an action that kills a person, that there's sort of less badness inherent in letting people die than in taking an action that actively makes people die. So it is worse to do something that kills the one person who is perfectly innocent than to simply let the otherwise inevitable consequences of the trolley run over the 5 people. Whereas the consequentialist would say that, one person dying is less bad than 5 people dying, so you should certainly switch. And the whole point of the trolley problem is not that there's a right answer to it. It's that we have different intuitions about the reasons why some things are good and some things are bad. And, if you don't find that one particularly convincing, there are other examples, like where you push a person off of a bridge in order to save someone's life and things like that. In fact, we talked about this with Joshua Green on the podcast. He does neuroscience as well as philosophy, and he's studied which parts of our brain light up when we think in deontological matters versus consequentialist matters. Anyway, I have not any idea of what this has to do with whether the right wing in the U.S. has been doing a form of consequentialism and whether or not that they appear to have won for this reason. I really am not so sure about that. I'm sorry that you're struggling with denialism. And, I don't think that the entire concept of reasoning is collapsing around us all. I think that it has always been true that there have been reasonable people, less reasonable people. There are fluxes and oscillations and changes, and sometimes the forces of unreason get the upper hand. Sometimes it's the forces of reason, and it doesn't happen automatically. We have to work to make it happen, but the forces of reason can get in charge once again. Henry Jacobs says, I'm not well versed on what true randomness is, or even if it's well defined. I know it's not universally understood among mathematicians. Under Everettian quantum mechanics, it just seems that there is no such thing as true randomness. Just pseudo-randomness, where we don't know the seed of the pseudo-random number generator. In this case, the seed is a vector in Hilbert space. The seed is partially revealed when we do an experiment. This revealing of a pre-existing thing sounds very Bayesian, as opposed to frequentist, where we assume true randomness. I heard of an interpretation interpretation of QM called cubism or quantum Bayesianism. I know a little beyond what I read in a magazine article about it, but the notion of an experiment there sounds like what I just described here. Is cubism the same thing as many worlds? Well, in many worlds, there is overall dynamics of the wave function, which is purely deterministic. So in that sense, there is no randomness. But there is randomness in where you are in the wave function if you're in a condition of self-locating uncertainty. If there's a splitting of the wave function into two branches and you don't know which branch you're on, it is truly random. There is no hidden fact that, there is a fact about which branch you're on, but there is no way for you to have known it until you actually look around and figure it out. It has nothing to do with a seed in the sense of a pseudo-random number generator. A pseudo-random number generator really isn't random at all. It just spits out a list of numbers that to all statistical measures will appear random if it's a good pseudo-random number generator. But this is not what is going on. There really are, when I do in many worlds a measurement of a spin, there really is a version of me on the spin up branch, a version of me on the spin down branch with 100% likelihood, and that has nothing to do with a seed that I have given it. On the contrary, in quantum Bayesianism, the whole idea of quantum Bayesianism and other epistemic approaches to quantum mechanics is to not care about one's idea of what is really going on in the universe, to really just say that the wave function is a way of making predictions. Cubism in particular, or quantum Bayesianism, emphasizes the idea that different people can have different ideas about what the wave function of a single physical system is because they've updated on different information. So the whole point of many worlds is to take the wave function as really physically real. The whole point of cubism is to not take the wave function as really physically real. So in that sense, they're quite different. In an operational sense, they're not that different. You may end up making the same predictions. Elise Cutts says, what's something you learned from a Mindscape guest that really surprised you or changed the way you think in a lasting way? It's a good question. I'm not great at remembering important lessons from people I've had on the podcast. Like when I'm podcasting with them, I'm focusing on what's the next question, is the audio quality good, things like that. So very often they say very interesting things and I don't always catch them or I don't always get a chance to remember them later on. One counterexample is an early podcast I did with Joe Walston. It's my favorite example for questions like this. He's a conservationist, and he works on, he has done work in various parts of the world, like literally working to conserve different environments and stuff like that. And later, at least at the time several years ago when we did our conversation, he was working an office job as a conservationist, trying to organize things in different ways and conducting studies, academic studies on how things are going. And he has this very provocative perspective where he says the thing that will save the environment is cities. And that sounds a little counterintuitive anyway, because cities are not the most conservation-friendly places at first glance, right? They're like a lot of concrete and steel and pollution and stuff like that. That doesn't sound like the conservationists' happy place. But in fact, the point he makes is that cities fit a lot of people in them and are actually quite relatively sustainable. Like just the fact that people live in apartment buildings, tall buildings, means that the heating costs per person are much lower in a city than in the suburbs or in rural areas. And what he imagines is a future where a lot of people live in cities, which, by the way, is happening. The world is becoming increasingly urbanized. And that leaves more and more room out there in the rest of the landscape of the earth for less spoiled parts of the environment. So he imagines a future equilibrium where there's a lot of people on Earth, but most of them live in cities, and most of the non-city places are pretty empty and left to nature, and you can enjoy them and appreciate them without hurting them in any obvious way. It's a little bit utopian, but it's something that we could aim for. And this whole idea of cities, even though I've lived in cities much of my life, I've gotten messages over and over again here on Mindscape that cities are just an incredibly important phenomenon from Jeffrey West, among other people, but also Will Wilkinson had a wonderful conversation on political polarization and cities. There aren't any Republican cities in the United States anymore. Republicans live in the suburbs or the rural areas. Of course, there are Republicans in cities, but they're almost never in the majority. There's a really strong correlation that wasn't as strong back in the past between political beliefs and the density of your neighborhood in persons per square mile. And Will connected those to personality traits. Some certain kinds of people tend to move to cities and certain kinds of people don't. And so, I think that's kind of the one big thing that I learned more than anything else, like an increasing appreciation for the spatial distribution of people here on Earth and how that affects our lives. Gog Halfront says, just like me, the universe prefers the lowest possible energy state. What is it that is preventing it from reaching absolute zero energy and just blipping out of existence? If this could happen before next Tuesday, I wouldn't need to see my accountant. So it's not actually true that the universe or any other system prefers the lowest possible energy state. If you have a system in an ordinary laboratory setting, right, like a pendulum or something like that, think about a pendulum rocking back and forth. In the real world, the pendulum will rock back and forth, but eventually, if you let it go for a very long time, it will stop rocking. It will just settle down to its lowest energy state. That's absolutely a true feature of things in the physical world, that eventually a big macroscopic system will enter its lowest energy state and just sit there. But notice that that system is not completely isolated, right? If you have an isolated system all by itself, energy is conserved, at least in laboratory settings and not in the universe. So that pendulum would just keep rocking forever. It has a lowest energy state, but it's not in it. It's never going to get there. The reason why it can get there is because we live in a non-equilibrium world with an arrow of time, and there can be dissipation. The pendulum can lose energy to its environment. The universe is closed. The universe can't lose energy to its environment, right? So, of course, as we already talked about, energy conservation is a trickier concept when it comes to the universe, but it doesn't really seek the low energy state in the same way that the pendulum does. What it does is it seeks its highest entropy state, which is absolutely something that it can do, and the highest entropy state of the universe turns out to be empty space. That's weird, right? That is not at all intuitive, but that's because gravity and entropy work together in intuitive ways. And that's exactly what's happening. The universe is expanding. It is emptying out. It is becoming emptier and emptier. But there's no sense in which it reaches zero energy, and there's certainly no sense in which it just blips out of existence. Indeed, the laws of physics, as traditionally construed, don't allow for things just blipping out of existence. They have to transform into something else. When it comes to the universe and quantum gravity, we are very aware that the laws of physics, as usually construed, might not be up to the task. So maybe the universe does either blip into or out of existence. We're not sure about that, but there's no reason to think that it should happen. Armin Delenian says, your episode with Steven Pinker explored how common knowledge shapes human behavior. The episode with Dmitry Timochko offered fascinating mathematical explorations of harmony. I suspect emotional responses to music are a form of culturally shared emotional language, rooted in our psychology akin to common knowledge. By the time children hear musical motifs, they often associate certain patterns with certain specific emotions through media exposure. What are your thoughts on how our sense of what sounds good is a repeatedly learned cultural framework rather than a universal mathematical truth? There's a couple things here. One, just to be sure that we're getting it right, common knowledge doesn't mean shared knowledge, right? Those are different things. Common knowledge is a technical term where not only do you and I have the same belief about something, but I know that you have the same belief as I do, and I know that I know that you have the same belief, etc. That infinite sequence, as we talked about on the podcast. But anyway, besides that, that's just a technical nitpick there. You probably understood it perfectly well. I didn't want the audience to get mixed up. I think it's a very interesting question about the relationship between cultural transmission of emotional language and, for that matter, just exposure to different musical forms and how we respond to them. I think it's 100% believable that there are musical sounds, or for that matter, expressions of any artistic modality that would not be good, not be well received by us if we had never heard or seen anything like it before, but become very precious and meaningful to us once we become familiar with it, right? In other words, I do think we can learn to appreciate certain kinds of music or other artistic expressions. But I don't think it's just random either. I think that the reason Dimitri did a very good job of kind of making the case that certain musical things sound good for good reasons, right? It's not just like anything would sound good if you heard it a lot when you were growing up or something like that. So, and I think that's fine. I think it's a combination of both things. I think that appreciating the detailed interplay between those things is part of the fun of learning why human beings act the way they do. Wayne J2 says, a question about applying Bayesian reasoning to the Fermi paradox. The absence of von Neumann probes flooding the galaxy is often used as a reason for thinking we are the only technologically advanced civilization. My own priors are that the existence of many instances of advanced life in such a vast universe is much more likely than the possibility of von Neumann probes. So I conclude that the fact that we haven't found any is actually evidence that such machines cannot achieve the capabilities envisioned in science fiction. What is your take on the absence of von Neumann machines, Dyson spheres, and other obvious alien megastructures as evidence that we are alone in the universe? Well, yeah, so for those of you who don't know or not familiar with the idea, von Neumann probe is a plan that John von Neumann, the famous mathematical physicist, cooked up, inspired by Alan Turing and Turing machines and his work on computation theory. Von Neumann showed that you could make a machine that had, he didn't build it, but he showed that you could build a machine that could construct a copy of itself, okay? That it had the instructions inside to build things that would let it, build itself, basically, build another copy, reproduce, if you like. So one of the arguments, as Wayne says, about the Fermi paradox is the following. If any technological civilization in the history of our galaxy had built a von Neumann probe that included the possibility of a rocket so it could launch itself across the galaxy, then it would be pretty easy for those probes to visit all the star systems, gather raw materials, duplicate themselves, and send out many more probes across the galaxy. You might think, why would you do that? Why would anyone have that idea? But the point of the argument is that the galaxy is pretty old, right? The galaxy is, over 10 billion years old, and it's not that big. I mean, it's pretty big, the galaxy, true, maybe tens of thousands or 100,000 light years across, but that's nothing compared to 10 billion years that it's been around, right? So it's very easy to get across the galaxy or to fill the galaxy while moving much slower than the speed of light. Indeed, assuming that the advanced technology won't let you just move at 0.99 the speed of light without any problem. So the point of this argument is that you only need to have it work once. Even if you have a million to one probability that any individual society will make von Neumann probes, if there's a million societies in the past of our galaxy, and remember, there's 100 billion star systems in our galaxy, so if there's a million intelligent technological civilizations, and one of them chooses to make these von Neumann probes, that would fill the galaxy, right? It's not a big ask, actually. Now, is it possible that the von Neumann probes are just technologically infeasible, even for very advanced alien civilizations? I guess it's possible, but I don't think that's really the most likely reason why something like this hasn't been noticed. In fact, I think it's perfectly possible that it's true that there are von Neumann probes all over the place, including in our solar system. We just haven't found them yet. The solar system is pretty big by human scales, right? Maybe there's one on the moon. We just haven't gone and actually unearthed it yet. Maybe it's under the ground. Who knows? I don't know. So I think that this is definitely an area in which our humility should come to the fore. We don't know a lot of the details, so it's hard to reason in any definitive way. But I will say that, there is one very obvious explanation for the absence, which is the absence of other technologically advanced civilizations. We might not want that to be the answer, but it is a very robust answer to all of these problems. And, Dyson spheres and other obvious alien megastructures, I think, are a little bit different. The Dyson sphere is something that you would build that would surround an entire star, collecting all of its energy for whatever purposes you have. But they don't self-replicate, right? Even if you decided to make Dyson spheres, if only one civilization did it and they didn't last very long, you wouldn't have a galaxy full of Dyson spheres. So I don't think that that's the same level of evidence for whatever level that might be. Nikola Ivanov says, the electroweak phase transition in the early universe resembles symmetry-breaking transitions in condensed matter systems like magnets or superconductors. To what extent do these systems share universal features? To a very large extent, actually. People do experiments. Wojtek Zurek and other people have led experimental programs that look at symmetry-breaking transitions in condensed matter systems as models of early universe phase transitions. You can even make like topological defects, cosmic strings, and monopoles, and things like that. Now, how universal are they? There's similarities and differences. A big difference is that in cosmology, the speed of light matters. These are truly relativistic systems, right? In condensed matter systems, there's a speed of sound that matters, which is typically a lot slower than the speed of light. There's a rest frame. The condensed matter system defines a rest frame by just existing, by sitting there in the laboratory. So the dynamics are never exactly the same, but the hope is that a lot of the robust qualitative features are going to be the same, and that, as far as we can tell, that seems reasonable. But on the other hand, we don't have a lot of direct experimental evidence about the symmetry-breaking transitions that happened in the early universe, so we're not sure whether we're correctly modeling them or not. Eric Bank asks a priority question. A recently published experiment reports a successful implementation of the PBR, Pusey-Barrett-Rudolph theorem, tested on actual quantum computer hardware, supporting the ontic view of the wave function. Acknowledging this is still very early days in quantum foundation research, my question is, if future larger-scale experiments conclusively show the wave function must be physically real, would that outcome falsify the many worlds interpretation of quantum mechanics, or could many worlds still survive in that scenario? So I know this is a priority question, but I'm a little confused by it because many worlds is the paradigmatic wave function realist ideal approach to quantum foundations. Many worlds thinks the wave function is real and ontic and there. That's what is making you believe in all these other worlds, because they're there in the wave function and we accept their existence as part of many worlds. So it's 100% possible to do experiments that would falsify many worlds, but the way that you would do them is to show wave functions collapsing all by themselves without being measured, like in Penrose's theory, for example. But finding evidence that the wave function acts in an ontic way, that is to say, it really does exist, is evidence for many worlds, not against it. Joshua Smith says, in the Fields chapter of Quanta and Fields, you explain that the nth excited state of a free quantum field, corresponding to n particles, is built up by taking the nth excited state of each plane wave mode and combining them. In contrast, consider a combination of the first excited state of one mode, the second excited state of another mode, the third excited state of another, etc., or any arbitrary combination. What would that represent in terms of particles? Well, it would represent a superposition of different particle number. So when you just take one or set of modes and excite them all to their first excited states, you have indisputably a quantum state with particle number 1 in it. But if you do what Joshua recommends, which is, take the first excited state of one mode, the second excited state of another, the first looks like one particle, the second looks like a two-particle state, and now you're in a superposition of both of them. So that's perfectly allowed. In fact, that's the generic case in quantum field theory. There's no reason to have a definite number of particles in your quantum state. Erkan Sertelli asks a priority question. In part of a previous solo episode on morality, you talked about various ethical reasonings for vegetarianism. Other than the environmental impact of the meat industry, you mentioned the act of ending animals' lives. You mostly discarded its moral significance, as these animals do not imagine long-term future prospects as opposed to humans. While I can agree with that sentiment, I was surprised that you did not mention the lifelong suffering that they may experience while they are alive. As a fellow meat eater who is sympathetic to the vegan cause, the biggest difference to me between an animal being farmed and being slaughtered versus one living in the wild and getting hunted by a lion is not that the wild one gets more future prospects, but that it gets to live freely in a free environment, exercising agency with whatever instincts, feelings, or thought processes it might have. Factory-farmed animals, on the other hand, are treated like machines for optimizing human profit, forced to live in overcrowded and unnatural conditions, force-fed, artificially inseminated, and forcefully separated from their cubs, etc. This doesn't apply to the entire industry, but in some cases it can even be argued that killing might be the kindest thing done to the animal. What are your thoughts on this perspective? I'm very sympathetic to this perspective. I don't remember exactly what I said on that episode, but I'm surprised I didn't say that because this is usually what I say, which is that it's the killing of the animals is not where I think the moral badness appears for exactly the reason you mentioned. But I think that causing pain and suffering to animals is very defensibly it is defensible to say that that is morally wrong. It's not defensible to do it. So one of the issues I have with with vegetarian and vegan arguments is that they do focus on the death of the animal. I wish they focused on the suffering of the animal. When I had the podcast conversation with Jonathan Birch about animal sentience, I thought that he put the focus in exactly the right place. And he made an argument whether or not you're vegan or vegetarian, you should still be against animal suffering, and we should do that, and we should complain about that. Now, there's a question, okay, if that's your moral stance, how best do you achieve that kind of thing? And I will refer you back to my previous discussion about you achieve it through institutional change, not through individuals trying to do things that make them feel good about their own moral choices. I'm all in favor of individuals doing things that make them feel good about their own moral choices, but I don't think that's the way to change the world. I think if you want to decrease animal suffering, change the incentive structures that farmers have to cause animal suffering, whether through laws or other forms of collective action. Kyle Cabasares says, I recently saw a PBS News special featuring Terrence Tao talking about the current funding situation for math and sciences in the U.S. He talked about being solicited by universities outside the U.S. and actually said leaving the U.S. to pursue his research has crossed his mind. My question is, have you also been solicited by other universities outside the U.S.? And do you think it would make any sense for you to personally continue your physics research in another country? Everyone's situation is different, and let's just say I'm completely understanding of people like Terry Tao thinking about moving to another country, given the current environment. It's not just sort of morally reprehensible what is going on in the United States right now, but at a very practical level, money's drying up, students are drying up. It's just become much harder to do research, and it's causing irreparable damage to scientific and mathematical research in the United States. On the other hand, I'm kind of old and settled myself. So I do occasionally get vague inquiries about my movability from one place to another. For the most part, I'm not that movable. I'm pretty happy where I am right now. You never say never because never know what's going to happen, but I'm certainly not looking to move anywhere. I'm trying to build up what is going on here at Johns Hopkins, and I'm very happy to do that. So I don't generally take those inquiries very seriously. I have in the past come closer to taking seriously inquiries from other countries, but that was before the current disaster zone that we're in right now, so I wasn't really involved with that. Moving to another country is a whole big deal, right? It's a young person's game, honestly, so it would have to be a very special decision, but also a very special opportunity. But also, a big part of me doesn't want to move. I want to stay and try to make things better in this country, right? Like if everyone moves as soon as things go bad, things don't get better. And I'm more invested. I have sort of more power and privilege than the average United States citizen. Much less than some people, obviously, but I have some, and I should use that to make things better here in the United States. That's what I would like to do, even if it's not necessarily the best place to do research right now. I mean, as I said, I think in some episode months ago, soon after the cuts to NSF and other things started happening, I happened to be in England. I guess it was last February, and I visited Oxford and other places, and multiple people said unprompted, like, oh yeah, I'm not going to let my graduate students go to the United States for a postdoc now. There's just no reason for that to happen. I've had, I organized a symposium, the Natural Philosophy Symposium back in May. Certain people were invited and would have come but didn't come because of the situation in the United States right now. It is really bad, and we're not exaggerating to say that it is really bad right now. There was a completely crazy proposal that just came out literally today as I'm recording this about it is illegal for any United States – it didn't happen. I don't think it happened yet. It's a proposal. It would make it illegal for any United States scientist to collaborate with other scientists from a certain set of countries, which included Russia and China and North Korea. The idea that a United States scientist, like a theoretical physicist, couldn't collaborate with another theoretical physicist from Russia, and it's retroactive. If you've collaborated with someone from one of these countries in the last 5 years, you can be thrown in jail or at least punished somehow. It's just bizarre and terrible. But nevertheless, I would rather stay and fight it rather than move somewhere else. That could certainly change depending on how things go. Jamie says, thinking about emergence, how might the properties of a micro-level theory like physics apply to a type 2 emergent macro system that arises from it, for example, politics? When we use aspects of the micro theory, like the idea of phase change, to describe behavior at the macro level, is this just metaphor, or are some of these elements potentially or necessarily real as you go up levels? Do type 2 emergent systems meaningfully inherit properties from the micro theory it emerges from, or are these cross-level similarities always just analogs? I hope this is not a not very helpful answer, but the answer is both. All those things can happen. I think the thing to emphasize, there's two things to emphasize, and I think other things can be worked out from there. Number one, when emergence is working well, sometimes it's not working well. Sometimes you're not exactly sure what's happening and you cross levels in your descriptions and stuff like that. But when emergence is working well, the higher level theories have their own rules. You don't need to refer to the micro level goings on to make sense or to make predictions about what is happening at the macro level. And those rules can be completely different, or they can be the same, okay? So the example of center of mass motion in Newtonian mechanics, Newtonian gravity, let's say. So you have the Earth moving around the sun. The Earth is made of 10 to the 50th particles. You don't need to know the position and velocity of all those particles to predict the motion of the Earth. You just need to know the position and velocity of the center of mass. But the rules for center of mass motion in Newtonian mechanics are exactly the same as the rules for the microscopic theory. The emergent level is planets and the sun. The micro level is atoms, but the kinds of rules in Newtonian mechanics are the same. Whereas the kinds of rules that you have for human behavior in politics are very different than the kinds of rules you have for particle physics or quantum field theory. Now, the fact that they can be different and often are different doesn't mean they can't also be similar. There can also be phase transitions. There can also be conservation laws. There can also be all sorts of different things. There's no prohibition that there is similarities between them, but there's no necessary inheritance from one level to the other. The Great Deceiver says, maybe this is a bit personal, but has a book or piece of literature ever brought you to tears? I think only once in hundreds and hundreds of reads did I lose it. That book for me was The Glass Bead Game by Hermann Hesse. What can you say about the power of fiction? I cry pretty easily at things, at good books, at movies, TV shows, whatever. But it's actually weird. If I think about it, I don't think about it that often. So I've been thinking about it since I read your question. What sort of chokes me up is actually not the sad bits, usually. I definitely have gotten choked up at reading books when things very sad happened. But what actually gets me is the more optimistic things. I'm a sucker for when the team assembles to save their friend, right? That always, tugs at my heartstring a little bit. And it's not maybe literal tears, but I'm like, oh, that's so awesome. But, I will cry at Wall-E just like everybody else does. The truly deeply sad pieces of fiction, something like, there's the movie Breaking the Waves, a Lars von Trier movie, deeply sad. It almost didn't have that much of an effect on me. I mean, the effect on me that it had on me was like, I don't want to watch this again. This is too sad. But it was almost like trying too hard to be sad. You know what I mean? It was like egregiously tragedy filled for the characters in the movie. And I was like, okay, yeah, that's everything bad is happening. Thomas Hardy would write these novels like Tests of the D'Urbervilles, which are just enormously sad. And I think that was actually pretty effective. He was enough of an artist that you're like, oh my God, yeah, that could happen and it would be this bad. And it's all just terrible and life is terrible. And, let me go watch The Good Place or something and, have some fun right now. But I think fiction is enormously powerful. I think anyone who has the sort of imaginative capacity to get caught up in a work of fiction, which is the overwhelming majority of people, can be affected by it. And I think that it's good that we can be affected by it. We can discover things about ourselves and about the world that are possible but much harder to discover by simply stating them. The power of fiction is that it can sort of lead you in that it trivializes it to say role playing, but you can sort of feel what is going on in a way that you don't feel it if you're just told things about human psychology or justice or anything like that. So all in favor of the power of fiction, despite the fact that I'm not very good at fictionalized mystery stories in my podcasts. Robert Davis says, is memory required for consciousness or self-awareness? I'm thinking of a time almost 40 years ago when I was in an automobile crash and my head hit the B-pillar off the sedan I was riding in. I recall going down the road prior to the crash, and the next thing I knew, I was sitting in the ER on a gurney counting backward by sevens from 100. I have no recollection of the crash, being extracted from the wreckage via the jaws of life, being in the ambulance, or anything in the ER prior to that. Obviously, I was interacting with the doctor, as I was saying, 86, 79, and so on when I came to. So I must have been showing signs of sentience in the ER. I have difficulty seeing how I could have agency without memory. This is a great question that people have thought about before. You're not coming to the world's most knowledgeable psychologist here, but I do have interest in memory and the arrow of time and not to mention the philosophy of agency and so forth. The answer is yes. Roughly speaking, you can have, the answer is no, the way you phrase the question, which is memory required for consciousness or self-awareness? No, it is not. I completely sympathize with why one might think it should be. And I think that would have been my first reaction, but you can collect the data. There are patients who basically have no memory, or maybe they have memory of things from a long time ago, but their short-term memory is completely gone, so they can't remember things that happened a couple of minutes ago. But they act like completely ordinary people, other than not being able to remember things like that. It would be very, very strange to claim these people weren't conscious. So I think this is a great example of where the data matter, not just thinking in the best way that we can about what we mean by consciousness, because I completely could have fallen for the idea that memory plays an important role in consciousness. Of course, it does in some sense. It affects our consciousness and our self-awareness in a very definite way. But also memory is multifaceted. There are memories and there are memories, right? Who's to say that someone who can't actually tell you what was happening 5 minutes ago isn't somehow affected by what happened 5 minutes ago in some more subtle way that we have trouble measuring? So I think that the short answer is memory is not required, but there's a longer answer is that there's a relationship there that is very subtle and worth teasing out that I'm really not that familiar with. Michael Bright says, when I was in high school, a history teacher I quite respected gave me a book called Diary of a Man in Despair, written by a German during the rise of Nazi Germany. In it, he wrote, the stupidity of an entire people in agreeing to this combination of corruption and inadequacy in its leadership is something else again. What I find odd is that I don't feel despair. I feel sadness, frustration, and anger at discrete decisions by this administration, but not despair. Should I feel despair? Do you? And is that a useful emotion? I think that the ability to occasionally feel despair might be useful. I'm not exactly sure what the use is, but I suspect that the fact that this emotion exists implies that it probably serves some purpose, even if I can't quite discern what the purpose is. I think giving into despair serves no purpose. Human emotions are a complicated amalgam of a lot of things going on, both psychologically and physiologically, and we can't always know why we're feeling certain emotions. But like you, sadness, frustration, and anger are absolutely the things that I feel, and I feel completely justified in feeling. I have not felt despair. I mean, I feel despair sometimes in the narrow sense that I feel helpless at certain things going on that I can't stop from going on, and I would like to. But it's not despair in the sense that everything is hopeless and I can't possibly do anything and it's all not worth fighting against. Like I just said a couple of minutes ago, I think staying and fighting is definitely the attitude I want to have about this situation we're in right now. So no, you should not feel despair, from my perspective anyway. You should be energized by the fact that all these bad things are happening. You should wonder why. I think that it is, and this is a little bit harder to pull off, I think, but when you see the kind of political fracturing that we have in our country, in the United States today, note to people 500 years from now listening to Mindscape, we are politically fractured right now here in 2025. When you hear certain things being said by certain groups of people that you thought were more sensible than that, it can be disheartening for sure. When you see institutions completely abrogating their responsibilities to stand up for what is good and true and right, that can be depressing very much. But, you have to figure – so anyway, sorry, I started saying we have to be honest and open about why it's happening. And sometimes that requires some combination of sympathy or empathy for the people that we're disagreeing with. Not sympathy and empathy in the sense that we agree with them, because we disagree with them and we can disagree very, very strongly. But it is good to try to understand their perspective. I don't think that that's out of bounds. In fact, I think it's very much necessary. I got in trouble once on Twitter, back when there was Twitter, when I said, the best way to understand people you don't agree with, even very, very strongly, is to read their own words and listen to their own explanations for why they believe these things. Even the worst, even the Nazis or the racists or whatever. And I thought this was like an anodyne comment, but I got such criticism for that. People are like, no, that would, we don't need to read all that. We know it's wrong. Okay, maybe you know it's wrong, but that doesn't mean you understand why someone thinks it's right. And I think that understanding why someone thinks it's right is important to making things better. We have to talk to people. We have to, persuade them. That's the point of being in a democracy. If you're going to complain about the collapse of democracy, you better set up a system where democracy can thrive. And that means talking to people and understanding where they're coming from. So there's a lot to do, Who has time to be despairing? There's a lot to do to fight against what's going on right now, even if we don't completely understand why it's going on. Joseph Eli, or Eli probably, says, I've just recently started familiarizing myself with Carlo Rovelli's work, and I'm particularly fascinated by his idea of explaining the low entropy of the early universe as being a perspectival phenomenon that we perceive only because of the particular coarse-grained variables that we interact with. This seems to dissolve the problem of explaining the low entropy of the early universe by making it something that exists only relative to subsystems like us, not a universal fact of the cosmos. I'm interested to hear your thoughts on this approach and on Rovelli's relational approach to explaining reality in general. So, Carlo, like I mentioned before, was one of the very first guests on Mindscape. I've known him for quite a good time. I love Carlo's work, even though I'm not a fan of loop quantum gravity especially. He's done a lot of good work in sort of physics and philosophy more generally. This relational stuff, I cannot get on the bandwagon. It is just very not the way that I think about these things. So in two ways. There's this very general idea that Carlo has that extends from gravity to quantum mechanics to thermodynamics about relational approaches, right? Like what matters is not this object or that object, but relationships between objects. That said that way, it sounds so harmless. Who could disagree? But, I don't think you can have relationships unless they're between objects, I think, or between things, very, very broadly construed. I think that you can't only have relationships. I'm not quite even sure what that would mean. So I guess I'm not sympathetic to the very starting point there. And in particularly when it comes to entropy, I think it's just misleading to say that we could coarse grain the universe in all sorts of different ways, and then we just happen to coarse grain it in the way that it looks like it was low entropy at early times. I think that's just incorrect. There are reasons why we coarse grain. I think that this is sometimes when we discuss the foundations of thermodynamics, we say like, oh yes, you coarse grain, and then if you start at a low entropy state, it goes up, and all that is perfectly sensible. But we don't talk about why we coarse grain in certain ways rather than other ways. And it's not just a choice. It's not just, kind of whimsical. There are physical interactions that we have with the rest of the world that more or less tell us how to coarse grain. Like when I look at the cream and the coffee mixing with each other, I see the cream in the coffee, like we were talking about before. I don't see the microstates. I don't see the individual atoms and molecules. But more than that, I can coarse grain in ways that give me a emergent description of the system. Averaging over regions of position space tends to give functional higher level emergent descriptions. Averaging over regions of momentum space tends not to. Different ways of coarse graining work better than other ways. This is what Dan Dennett, another former Mindscape guest, called the real patterns underlying the world. So I think that Carlo's approach sort of doesn't give enough credit to the real patterns, the real reasons why we coarse grain one way rather than another way. So I think explaining why the early universe has a low entropy in the coarse grainings that we actually use is a very, very high priority physics problem. Gilbert Rodriguez says, how much of one's lifespan is worth sacrificing for the maximization of pleasure? It's obviously imprudent to prioritize instant gratification above all else, and similarly to prioritize longevity above all else. Pleasure and longevity are also not mutually exclusive, but there are many practices that clearly decrease the average lifespan while enriching one's experience, e.g. eating tasty food, drinking alcohol, base jumping, driving. Would you give up 1 year of your life to increase participation in such things, 2 years, 10 years? This is a good question, and I don't know what your expectations were here, Gilbert. I'm not going to give you a quantitative answer. I'm not going to say 3 years. I'm a big believer in quality of life, right? I'm not just a big believer in quantity. And I think that this mostly has super important implications for the end of life, where I think that, our society has this idea that we should just prolong life as long as possible. That was another very early podcast conversation we had with Megan Rosenblum of the death of the sort of good dying movement, where, we should improve the end of our lives to make them about quality rather than quantity. But in the middle of our lives, where we're deciding, should I eat the healthy meal or should I have pizza, given that pizza will make me happier, but the healthy food will make me live longer, I think that's sort of a rolling condition that you sort of make up those decisions from moment to moment. And indeed, I don't know, that's what I do. Like some days I'm feeling good enough that I can eat all the healthy food and I can forswear all the bad stuff. Whereas some days I'm like, give me that pizza. I just need it. It's been one of those days, right? And I think that that's a perfectly legitimate way to live. I think I'm with Aristotle and with Buddha, for that matter, about balancing and about finding a pleasant medium of these things. It also helps for me personally that things like base jumping or climbing sheer mountains and putting myself in non-trivial amounts of physical danger holds essentially no attraction. I'm just not interested in doing those things. So it's easy for me to say, no, I don't want to, go jump out of airplanes because it'll be exciting. Like I get it that it's exciting, but it's not that exciting. I mean, you fall and okay, but and it can be very dangerous. So no, I don't want to do that. Easy for me to say. Whereas tasty food, drinking good drinks and things like that are important to me. And so I am willing to give up some of my lifespan for them. I would feel very differently if I thought it was a huge amount of lifespan I was giving up, or if I felt that doing some activity had a large probability of lowering the quality of much of my lifespan. One big problem here is that all of these predictions are very fuzzy, right? Like, okay, so I have a pizza. Does that mean that I have one less day on average? I mean, Is it an average, or is it a huge span of possibilities that I'm entering into here? Are we sure that having the occasional pizza doesn't make me live longer? So these are very difficult things to do. I think we kind of, most of us know that there's a generally healthy, productive way to live that allows you to enjoy some tasty food and some alcohol, some driving, all without abusing any of those privileges. And that's what I would like to do, a sort of acceptable amount of risk in order to live a productive and happy life. Sid Huff says, I really enjoyed your talk with Mary Roach. The discussion about replacing body parts makes me wonder at what point, if ever, would a human person become someone or something else if enough body parts were replaced? The ship of Theseus paradox comes to mind. If we had every body part except our brain replaced, are we still the same person? What if a partial or entire brain transplant in the far future, presumably, were to become possible? What if a portion of a person's brain was replaced with a chip? Yeah, these are all good questions. David Chalmers, I read it from David Chalmers. I don't know if someone else made it up, but had the idea of what if we took one of your neurons and replaced them with a little computer chip that did exactly what the neuron did? So your activities are no different. Would you be the same person? You're tempted to say yes, but then you know what's going to come. He's going to replace all the other neurons until you have no more neurons left, nothing but computer chips. Are you still the same person? I think that the philosophically correct answer to this is that you're never the same person. Without even replacing body parts, I'm not the same person I was when I started doing this podcast, right? Because I've had different experiences. My atoms are slightly different in slightly different places. I'm a little bit older, thirstier or whatever. But I'm continuous in some ways, and one can, and again, philosophers do this. Derek Parfit wrote a lot about personal identity and continuation through time and things like this, did thought experiments with transporter machines and what have you. There's no once and for all right answer to any of these questions. The question is not, are we the same person? The question is, what are the advantages of thinking of that person as one entity versus a completely different entity? And I think that if you just replace a couple of body parts, the advantages of thinking about that person as a continuous being are very obvious and very clear. And of course, you can play the science fiction games to get to places where it is less clear. Maybe we'll have to collect some data about that, but I can foresee that the boundary is going to be fuzzy. And the question is not do we cross some threshold and we're no longer ourselves? The question is, what treatment do we give to such people in the future? I think we're going to find out. I think it's not really a philosophy question. It's a practical question. There will be legal and social implications that we're going to have to think through. Patrick Spencer says, you mentioned at the end of the fine-tuning episode, if the proton-neutron mass ratio were pi, we should look into that. What do you think of the Koida formula, which says that a simple function of the charged lepton masses is 2/3? It gets good Bayesian points for being much more accurate. They threw away an adjustment term after better mass measurements, and now seems uncomfortably accurate for it to be random choice. It's correct to 6 significant figures. More broadly, where is the line between numerology and science? How can the strength of formulaic coincidences be quantified? This is a great question. I love this question. And I think that it's a good illustration of exactly the difficulty of being too cut and dried about these kinds of questions. So the Koida formula was proposed, I forget when it was proposed, but I looked it up. I knew what it was. So here it is. Here's the Wikipedia page. It has its own Wikipedia page, KOIDE formula. Yoshio Koida proposed it in 1981. And it's a formula relating the mass of the electron, the mass of the muon, and the mass of the tau lepton. And it says that ME, mass of the electron, plus mu plus m tau divided by the quantity square root of me plus square root of mu plus square root of m tau, quantity squared, equals 2/3. Okay? So on the one hand, that is not the most obvious relationship that you would just go out there and guess. But on the other hand, it's not horribly complicated either. I believe, as the Wikipedia article states, just from the numerical or I guess algebraic form of the equation, that ratio of me plus mu plus m tau to the square of the quantity square root of me, square root of mu plus square root of m tau must always be between 1/3 and 1. Okay, there's no chance it was going to be 500. There's just no numbers that would give you that. It's a number between 1/3 and 1, and it's very, very close to 2/3 in the real world. Okay, and in fact, Wikipedia says it is 0.666664. Okay, so it's not exactly 2/3. It's not 2/3 within the experimental error, but it is pretty darn close. So how seriously should we take that? Apparently Koida came up with it, not by guessing, but by actually having a theory that predicted it would be true, and apparently it did pretty well. And I think that the answer is we should take it a little seriously. We shouldn't be, look at it and go, oh, yes, that must be a fundamental fact of nature. But the fact that such a relatively simple formula works is worth for further study. Note that it works for the leptons, not for the quarks. And note also, and this is a more subtle physics point, readers of Quanta and Fields will know we have such a thing as the renormalization group. We know that when you talk about the mass of a particle, that's not a number. It's a function of the energy at which you measure it. So you have to be very, very careful to define precisely what you mean by the masses of the particles, right? When people try to derive the fine structure constant from numerology, it doesn't work very well because the fine structure constant changes with energy scale at which you measure it. So all of these are sort of caveats to point at the formula, but its success, I think, does give you a little bit of a motivation for looking for explanations of it. It's not quite as simple as if the proton-neutron mass ratio were pi, right? That's a little bit more blatant, and it suggests there should be a very simple thing. That's how theoretical physics goes, right? You look for the clues. Some of those clues might pan out and say, oh, okay, I see where that came from and I can now explain it. Others might just remain coincidences or go away. There's not a line between numerology and science. There are clues that pan out and clues that don't pan out. Alex says, recently I've seen what was claimed to be a picture, in quotes, of a particle. Physicist Aneta Stodolna has a picture of an electron's orbital inside a hydrogen atom, and there's also some claims to have pictures of atoms out there on the internet. If particles are just a way to think about locations within a field, what exactly are we looking at? Also, aren't electrons and atoms smaller than the wavelength of light? How do you get a picture? It's a good question. I'm not exactly the person to ask because I don't know exactly what was done in this particular example, but I'm familiar with the example. I've actually used these pictures of atomic orbitals. The idea, if you haven't seen these pictures, is it's basically supposed to be a picture of a wave function. That is to say, in an atom, electrons fall into orbitals, and the different orbitals have different shapes. And you can't, according to the rules of quantum mechanics, simply take a picture of it. That's a little bit of marketing to say that we've taken a picture of it. You can't just take a snapshot of the wave function of an electron. What you can do is measure the position of the electron, maybe to some precision, which is not perfect because atoms are very small and this is very hard to do. But if you're a really good experimental physicist, you can basically infer as the result of some measurement where the electron was in the atom. And then you can do that again and again, right? So you can build up a picture of what the wave function of a single atom would have looked like from doing multiple measurements. And you can try to make the measurements as non-interfering as possible, et cetera, et cetera. So it's not a picture in the standard sense, but I do think it is a data-based representation of what the electron wave function looks like in an atom, and in that sense, it's perfectly legit. Jonathan Gordon asks a priority question, who says, I would like your thoughts on using the transactional interpretation of quantum theory as a metaphor for Carl Rogers's testing for understanding. In John Cramer's theory, which is the transactional interpretation, the retarded wave and advanced wave perform a handshake. This understanding between the two interacting elements allows creation to unfold. In Rogers, or is it Roger? I don't know. Carl Rogers. Rogers' active listening practice. A human speaks and the listener reflects back what the speaker says, and the speaker confirms they were understood. So I'm going to be disappointing in two ways. One is I don't know almost anything about the transactional interpretation, and I don't know almost anything about testing for understanding. So I can't say anything about whether or not it's a good metaphor for it or not. Even though it's a priority question, all I can do is tell you that I'm going to give my best try at answering it. And in this case, I have literally nothing to say, almost nothing to say. I will say the following thing. I would be shocked if there was any useful analogy here, other than the existence of something like a handshake, Maybe that's a good metaphor for something, but that's a metaphor both for this psychological technique and for the quantum mechanical theory. It's not that the quantum mechanical theory and the psychological technique are good metaphors for each other. I just would caution against using quantum mechanics in particular as a metaphor for almost anything, because quantum mechanics is very hard to understand. And even if you do understand it, it's very non-intuitive. It's very non-everyday. It would be very strange to reach for quantum mechanics in a search for an analogy for something, because quantum mechanics is not in our bag of things that we understand well. The idea of an analogy is you take something you don't understand and you analogize it to something that you do. In this case, I don't understand either one, so it's not very helpful there. But the specificities of quantum mechanics, the specific way that you have wave functions and entanglement and complex numbers and measurement and decoherence, these are generally not there in any of the things you're trying to draw an analogy to. So I think those analogies get us in more trouble than they are useful. Marie Roscu says, many lectures, talks, and podcasts about quantum mechanics begin with describing it as weird, counterintuitive, bizarre, or things like that, as I just did. So fair enough, Marie. Like issuing of a warning. But no one starts a lecture on Newtonian physics with counterintuition warning, e.g., we don't feel the Earth moving, that's weird. Shouldn't we retire these stereotypical phrases about quantum mechanics? What's your opinion? No, I think maybe we should start using them in talking about other areas of physics. But, it's not like they're universally counterintuitive. We have an experience of the world. We have an experience of the world in our everyday lives where certain things happen, certain things don't. We make a causal map of the world around us, which philosophers sometimes call folk physics, right? It's not a very well-developed theory. It's not rigorous or anything, but we know apples fall from trees. They don't fly up into the sky when they leave the tree. And that's where our basic intuition comes from. It's pretty close to Aristotelian physics, because Aristotle didn't have a lot of super high precision data to work on. He was going on everyday experience when he came up with his theories. And we have things like, things go to their lowest energy states, right? That's part of intuitive physics. In an isolated system, if you learn classical mechanics, things don't go to their lowest energy states. They have energy conservation, so you have to update your intuitions a little bit. It's just that when it comes to quantum mechanics, the update is much more massive, right? For Newtonian physics, you're like, okay, the pendulum will, in the real world, eventually stop rocking back and forth and come to rest. But I can kind of see that if you say there's no friction and there's no air resistance, it would just keep rocking forever. Okay, I can accept that. Whereas the electron can be in multiple places at once. There's just not a very good intuitive thing to latch on to. So I think it's perfectly fair to say that quantum mechanics is weird, counterintuitive, bizarre, with respect to our everyday expectations. Of course, by itself, quantum mechanics makes perfect sense. But compared to how we grow up in the world, it doesn't. And I think that noting that and moving on is a perfectly legitimate rhetorical move when you're talking about quantum mechanics to general audiences. Tim Converse says, I really enjoyed your solo episode on fine-tuning. It's one of my favorites. I feel like I understood much of it, but not the very first step. I understand that if constants of nature have surprising values, we're more likely to think that they are fine-tuned. Yet, as a non-physicist, I don't think I have priors on the values for some of these constants. If you tell me that some dimensionless constant c has, for some integer m, either the value m or the value m divided by 10 to the 120, I wouldn't know which value I should be more surprised by. I take it that some physicists have a natural expectation that some constants should fall into a natural range, where that range is somehow related to the Planck mass. Could you help me understand that first step? Well, I think you put your finger on something that is a little bit tricky there. I did try to talk a little bit about it in the episode, but I didn't want to go too much into the physics there. Where do we get these expectations? We do have them. It's 100% true. And we should have them. If you didn't have any expectation at all, you would never be surprised by an experimental result. You would just say, oh, that's the result, and you would move on. But as I tried to make clear in that episode, the role of being surprised by these fine-tunings is that it gives us motivation to find an explanation. We think of it as a clue that might help us invent a better theory. The invention of inflationary cosmology is a classic example. It was motivated in part by fine-tunings of the geometry of the universe and the homogeneity of the universe as well. And Alan Guth came up with an explanation for those two things. It may or may not be the right explanation, but it was certainly a very clever scientific idea. So where do these expectations come from? It's usually from effective field theory. I talk a little bit about this in Quanta and Fields, but the idea is it's not just that everything should be the Planck scale. That's not quite right. But it's that everything in field theory does talk to everything else, right? Like every field pushes around every other field, either directly or indirectly. And when you have a quantity that you're measuring, like let's say the mass of the Higgs boson, the mass of the Higgs boson is a classic example of something that appears to be fine-tuned. Its natural value, as we say, its natural value is up near the Planck mass, but its actual value is 10 to the minus 15 times that or something like that. Where does that come from? Where does the expectation come from? Well, in reality, it's not just a number that God gives you. Here's the mass of the Higgs boson. Rather, there are a lot of effects that go into the number that you and I measure at the end of the day as the mass of the Higgs boson. What you call the Higgs boson is an excitation in a field that is constantly talking to other fields. There are Feynman diagrams with virtual particles in them that connect the Higgs boson to the top quark and the gluons and everything else in the universe. And so you can think of the number you're measuring at the end of the day as a combination, as a sum, as literally adding together a bunch of other numbers. And these other numbers often take the form of integrals over different momenta of all these virtual particles, from one energy scale to another energy scale. So at the end of the day, the way that we think about these numbers is we're measuring the sum of a bunch of contributions at a certain energy scale. And it would just be weird, we think, that if all of these apparently unrelated contributions canceled against each other so that the total sum of their effects was a number that was much smaller than any of the individual ones, right? And so we do have a feeling from effective field theory about where the natural scales for different dimensionful quantities should be, and then their dimensionless ratios are generally going to be either 1 or something of order 1, or we'll have a good explanation for why not. Like in QCD, there's a natural sort of running of the coupling constants that explains why the QCD scale can be so much smaller than the Planck scale. There's no such explanation for the Higgs boson, at least not in the standard model of particle physics. None of this is to say that that expectation can't be wildly incorrect. I mean, it is incorrect. We got to get the wrong answer, right? So it's not like this is a theorem or anything like that. It's just a setting of an expectation. If you want to say, well, I didn't have that expectation, then I can say, okay, you're allowed to not have that expectation, but I might be motivated to look for a theory to explain it, and you might not be. And if I find the theory to explain it, I win. And if I don't, then you win. And that's the game that we play by being theoretical physicists. Going to group some questions together. Going Gödel's incompleteness theorem is going to appear in most of them. So Marek Borik says, Gödel's incompleteness theorem shows that even in mathematics, there are true statements that can't be proven within a given formal system. I wonder if something similar might apply in physics, especially in quantum mechanics, where certain aspects of reality seem true in an empirical sense, but resist derivation from first principles or a fully logical chain of reasoning. Perhaps it could even be one of the possible explanations for the wave function collapse, that we cannot fundamentally prove what happens. Do you think there's any merit to this idea? TCMD says, could you share your views on how the intersection of underdetermination, Hempel's dilemma, and Gödelian incompleteness might constrain our practical prospects for a deterministic theory of everything, or for any closed, self-sufficient set of physical laws that function as one? And then Paulina Vino asks a slightly different question, but it's still related. Theoretical physics and foundations of mathematics are two areas of inquiry that seem to appeal to people that have at least partially accepted that certain truths are somehow inaccessible or inexplicable. Do you feel like you have enough experience interacting with folks interested in both to make some overarching generalizations and similarities or differences in personal values and characteristics of those that choose one over the other? So let me address the first two first. And I'm sort of not sympathetic to the general view that is being suggested here, the idea that somehow either from philosophical questions about underdetermination or mathematical formal issues like Gödel's incompleteness theorem, that somehow these are obstacles to us finding a full and complete physical description of the world. And the reason is because the process by which we go about proving mathematical theorems and the process by which we go about constructing physical models of the world are entirely different, are very, very different kinds of processes. Even within mathematics, it's not as if Gödel's theorem says, here is a true thing that you can never know. Right? It says, here's a true thing you can never prove. Indeed, assuming that your formal system is complete, Gödel told you the thing. He told you the statement that you can't prove. It's a statement that is sort of isomorphic to saying, I cannot be proven, right? It's the liar's paradox. So it's not as if it's unknowable in any sense. It's just unprovable. And I think that there's a general move in the foundations of mathematics to move away from theorem proving as the central thing that mathematics does. Like in working mathematics, proving theorems is still the thing that mathematics does, but as an axiomatic foundation, it might not be the best way to think about things. Rather, thinking about models or categories or something like that might give us a more complete grasp on the entire foundations of mathematics. This is not something I'm an expert on, so don't believe me about this, but that's the impression that I get from talking to the people I know about. But anyway, finding a theory of the universe is, as we discussed earlier in the AMA, mostly about guessing and then checking. And you never know whether you're right with 100% confidence, right? So the fact that there are statements in formal systems that I can state but not prove, and nevertheless I think they're true, what does that have to do with my ability to guess F equals ma or Einstein's equation or something like that? I don't think it has anything to do with it at all. So I don't think that it prevents us from finding the right deterministic theory of everything, or if there is such a thing. And I don't think that it applies, it helps explain why in quantum mechanics certain things seem weird. I don't agree that in quantum mechanics certain aspects of reality resist derivation from first principles. I think I can derive them all from first principles in quantum mechanics. And then to Polovino's question, again, I wouldn't quite agree with the characterization that theoretical physics and foundation of mathematics people have at least partially accepted that certain truths are somehow inaccessible or inexplicable. I don't accept that. I mean, maybe it's true. Maybe certain truths are somehow inaccessible or inexplicable. I don't think I'm anywhere close to the boundary of having said almost all the truths except for the inaccessible ones. So there's plenty of truths that we haven't found yet that are perfectly accessible. We just haven't accessed them yet. So I don't think that's quite, and also in foundations of mathematics, Gödel's sentence is very accessible. It might not be provable, but it's right there. He wrote it down. So, I think that it's hard to do theoretical physics and to find truths about the universe, but I think that, reaching for some mathematical, philosophical explanation for why it's impossible, I'm very unsympathetic to that. I come across it occasionally, and I'm always like, why would you ever think that? I'm much more impressed with how much we have done than in the apparent inability for us to do everything. David Kudaverdian says, on many different occasions, you've said that the many worlds interpretation doesn't bring any new insights into purported moral theory. I have trouble distinguishing whether this is your belief or you're saying that it is inconceivable to think otherwise. To me, it is not clear why exactly we should forget, in the purported moral theory, that all the outcomes of a quantum experiment are real rather than merely probabilistic. Imagine the following experiment. Suppose you genuinely believe that there's a 99% probability that a certain mathematical conjecture is correct. Then an omniscient alien comes to you and you make a bet with him, and this mathematical statement turns out to be false. You put your cat to sleep. In this situation, even if you're a many worlds believer, you're 100% sure that there will be only one outcome of this experiment. And you might want to assign a different moral connotation to this experiment than to the analogous one where you toss a quantum coin in which both outcomes, cat sleeps and cat awake, are real. Maybe, look, I have said, I certainly don't think, to answer your actual question, that it is inconceivable to think that many worlds has moral implications. We talk a little bit about this in the podcast with Laura Buchak, where I said that, maybe something like risk aversion or, that kind of moral attitude might end up with different consequences in many worlds than in a purely stochastic theory. Not that I know that it does, but I'm open to that possibility. So I am open to that possibility. But I don't think that your thought experiment is an example of this. For one thing, I think that maybe there is an incompleteness in the statement of the the scenario. The omniscient alien makes a bet with me, and if the mathematical statement is false, I put my cat to sleep. But you didn't say what happens if it's true. Like, what reward do I get? What am I balancing here? But more importantly, I think this is just an example of people not taking 1% chances very seriously, right? I take 1% chances very seriously. Apparently, I'm guessing that what you're thinking here is knowing that there would be 100 worlds and having the cat asleep in one of them. And maybe I think by put your cat to sleep, I think this is a euphemism for having them euthanized, having them killed, right? Having that happen in one world and not happen in 99 worlds is, viscerally supposed to be worse than just having a 99% chance of them being okay and a 1% chance of them dying. And that's what I don't really agree with. And so here's an argument for why I don't agree with it. Imagine that space that we live in is very big, right? Imagine the universe is very big. And imagine there's no weird multiverse or anything like that, but it's just big and it just goes on forever and ever and ever, literally infinitely big. Then there will be, far away, as Max Tegmark and others have mentioned, there will be examples of us here on Earth that are very, very similar, indistinguishable from what's going on here on Earth, just because space is infinite and there's kind of a finite number of things that can happen in any one region of that space. So in that case, there will be many, many copies of me doing this experiment, right? And if I really thought that, it was a 99% chance versus a 1% chance, then what that means is in those many copies, there is, I should think of this if it were truly random. Like in this case, it's not truly random. It's a mathematical theorem. I get that. But if I truly thought that it was an objective chance of 1% bad thing happening versus 99% good thing happening, then in that big universe, it would be 1% of the instantiations of me that would happen to. And if that is worse in my mind than only one instantiation of me existing but having a 99% versus 1% chance, then I think I'm just not reasoning correctly. I think that I'm just not giving enough weight to the 1% chance. And people can disagree about this. That's fine. Yeah. I mean, in my book, Something Deeply Hidden, I literally gave an example of a moral rule that would be different for many worlds versus other approaches to quantum mechanics. I just didn't think it's the kind of moral rule that I would accept. All right. Julie Evanoff says, my question is about dilution, maybe at its essence. When I steep tea, for instance, if I use only a little hot water and steep it very strong, then add plain hot water to make it less strong, is that fundamentally different than steeping the full amount of water less strong? That extra hot water that I would add to dilute the strong tea, does that lack some essence that changes the water when it actually is interacting with the tea leaves? So I kind of picked this question to answer just to point out that I'm literally the world's worst person to ask this question about. And I mean, I know why someone would think that I would have an answer to it, because I'm a physicist and I think about these things, but I'm the kind of physicist who thinks about where the universe came from and the fundamental laws of nature, not about steeping tea leaves in water. And I have enormous respect for the fact that the kind of intuition and rules that you get very far with thinking about the fundamental laws of physics don't always give you immediately correct answers to these everyday circumstances like putting tea into water. So I think that the initial intuition here is that it doesn't matter if you put just a little hot water and steep it very strong, then dilute, versus just putting the tea bag in a whole cup of hot water. That sounds to me like the same process going on. However, to be very honest, there is a physical difference, right? The density of water versus tea is different in one example versus the other. I don't think that makes any difference to what is going on during the steeping of the tea, but I do not know enough about the chemistry of steeping tea to actually say for sure. What I would recommend is that this is a very affordable experiment to do. You should do it and report back. Let us know whether it made any difference. Mike says, do you or other physicists sometimes use LLM tools to quickly pre-read, summarize, or assess a new paper when it comes out as a convenience? Do you find it usefully accurate or inherently unreliable? No, I don't use it for that. I do use LLMs. I'm not anti-using LLMs, but that is not a use I would put them to, precisely because, it depends on the paper, of course, but the papers that I find most interesting are the papers that are saying something very subtle and very new, like they haven't been said before, right? Something a little bit different than your expectations. And again, LLMs are not thinking. They're not doing what human beings do. They're trying to say what is the most natural thing to appear next in this sentence. When I did visit Elon Musk's Grokpedia, and of course I looked up my own entry there because I can easily check the accuracy of the entry about me. And it was very long, much longer than the Wikipedia entry, and it was, mostly correct. It was much longer than it needs to be, honestly. It should be way shorter. That's the problem with having things that can produce arbitrarily large amounts of text. But it was, very wrong in very blatant ways in the places it was wrong. But sorry, I shouldn't say blatant ways. It was wrong in ways that someone who didn't know all the details would not be able to notice. Because the kinds of mistakes that an LLM makes are sort of regressions to the mean. Right? The LLM is filling in things that it thinks would naturally go well with the sentences it's already read. So when it talks about my PhD thesis, for example, part of my PhD thesis involved topological defects, textures, and other topological defects in the universe. And Grokpedia says Carroll, predicted the gravitational wave output of collapsing topological defects. So no, I did not do that. But it is something that someone would do. It would be very natural to do that kind of thing. So those are the kinds of mistakes that the LLM makes. It's a different kind of mistake than a human being would generally make. So for reading a new paper that is saying something really difficult and interesting, that's exactly what you don't want the LLM to be summarizing it for you. If it's something very straightforward that is commonplace, if there's something everyone agrees on and you want to learn it, you don't know it, but you want to learn it, that's when LLMs are great, right? Educate me about this well-known fact that I just happen not to know. That's what it'd be good for. There might be some use for them. They're going to get better over time, right? So it might be useful for certain things like that, but neither I nor anyone else that I know of uses them. Maybe there are some people who use them for that. I'm not familiar. Okay, we're at the end of the AMA. The last question comes from Jonathan Kleiman, who says, I studied philosophy in undergrad. I had a professor named Mario Bunga for philosophy of science. He was incredibly brilliant, and I deferred to him in all things unintuitive about the nature of reality. But now he's dead, and you're my go-to. How do I reconcile the fact that you disagree so strongly on many worlds? It's not even that you differ on the ontology itself that spooks me. It's the fact that you use the very same razor of Occam that has led you to opposite conclusions. You to the cleanliness of many worlds, and him to that of only one. Well, thanks for the implicit compliments in there. That's very sweet of you, Jonathan. Of course, part of the answer is you shouldn't be deferring to anybody. You should be listening to the arguments and judging them. If you're already at the point where you studied philosophy in undergrad and you know what a wave function is and you know the arguments for and against the simplicity of many worlds, I think that you know enough that you should be drawing your own conclusions here. Look, it depends a lot on what your starting point is. When this is always true, right? When you don't have the definitive answer in a scientific controversy, different people are going to have different commitments to different ways of viewing the world, and that's going to lead them to different conclusions about controversial topics. So one big thing is, do you think the wave function represents reality or not, as we were talking about before in cubism versus many worlds? If you think that the wave function is just a way of predicting outcomes, then you might very well, I would get why you would think that many worlds is profligate, because it has all these worlds that you don't need. To me, that's just a completely untenable point of view, because you're kind of abandoning the scientific effort to understand reality. You're saying, like, I don't want to know what happens in reality. There's no such thing as reality. All there is me making predictions for measurement outcomes. What is this you? What is this measurement? What is this outcome? There has to be a reality there that you're describing. So I think that the whole philosophy of it is a little bit internally inconsistent, or necessarily provisional. I mean, basically saying, like, of course you could have an attitude that says, of course there is a reality, I just don't know what it is, so I'm not going to say anything about it. I'm just going to, in the meantime, be a quantum Bayesianist or whatever. And, okay, but I have a theory that explains reality, so I'm not going to be very sympathetic to that point of view. If you think that the wave function is real, then I think that you have essentially zero justification for thinking of many worlds as ontologically extravagant or non-simple, because the wave function is there. The wave function, if you think that an electron can be in a superposition of two different spins, then there's no more heavy lifting to be done to think that the universe can be in a superposition. It's the same math. The Hilbert space isn't any bigger in many worlds, and it's just one vector in Hilbert space. It's just that vector can represent many simultaneous branches of the wave function. The only question is, does the dynamical evolution of the wave function, given by the Schrödinger equation, lead us to many separate branches actually existing? And there the answer is crystal clear that it's yes, right? So if that's one's perspective, that the wave function does represent reality, and you just don't like the existence of all these worlds, I think that's just a mistake. I think that is actually just, letting your visceral reaction or your intuition that is trained, as we mentioned, from everyday experience in a single branch of the wave function and blindly applying it to a circumstance that it just doesn't apply. Even if you believe the wave function does represent reality, that doesn't necessarily mean you have to be a many worlds person. There are plenty of other approaches where it's ontic, but you don't get the many worlds. But they're all clearly more complicated. They're all more jury-rigged, and there's all these extra equations and ontological elements or whatever. There's really no competition there. So I think that you either think that many worlds is simple and viable. Maybe you don't think that it's the most likely thing, but you think that it's simple by Occam's razor standards, or you just abandon the idea of describing reality in any known quantum mechanical formalism that we have at all. To me, that's a pretty easy decision. To others, they might think differently, and that's good. I'm glad people think differently. I'm glad people care about these things. I think they care about them more and more. One of the nice things about the work that I've done over the years is I do think that I'm nudging younger people to care more about the foundations of physics in ways that, not just me, like I certainly am not saying that I'm the major effort here, the major influence here, but I'm part of a movement to make people care about these questions a little bit more carefully than they do. And I think that's going to have a healthy impact on physics going forward. Small, but, healthy so far as it goes. So happy to see that. Anyway, as always, many, many thanks to everyone out there who supports the Mindscape podcasts. I hope you enjoyed this month's AMA, and we will talk to you next time.